I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than have answers which might be wrong.
In the silent vastness of space, a discovery has shattered our understanding of the nearest star system. The James Webb Space Telescope, humanity's most advanced eye into the cosmos, has uncovered something unsettling in Alpha Centauri. What was once thought to be a quiet, familiar neighborhood now reveals signals and anomalies that defy explanation. As scientists scramble to interpret these findings, the implications ripple far beyond the laboratory. This isn't just about new knowledge. It's a stark reminder that exploring the universe demands humility, responsibility, and an awareness of the profound impact our curiosity can have. With each revelation, we are reminded that the pursuit of cosmic understanding is as much about ourselves as it is about the stars. What secrets has the Webb uncovered, and what does it mean for our place in the universe? For centuries, the stars have beckoned humanity with their silent, shimmering presence, inspiring wonder and curiosity. Among these celestial neighbors, Alpha Centauri has held a special place in the story of astronomy. It is not just our nearest stellar neighbor. It is a shining beacon that has guided explorers and scientists alike through the ages, shaping our understanding of the universe beyond our own sun. Long before telescopes pierced the night sky, ancient observers gazed upward and wondered about the nature of the stars. They noted the brightest points of light and imagined stories and meanings behind their flickering. As centuries passed, those early observations laid the groundwork for a more systematic pursuit of knowledge. The dawn of the telescope in the 16th century marked a turning point, revealing that what we see with our naked eye is only a fraction of the universe's true complexity. Alpha Centauri gained particular significance during this period. Because it is the closest star system to our Sun, astronomers saw it as a promising target for early attempts to understand other worlds. In the late 18th century, the renowned astronomer Thomas Wright speculated about the possibility of planets orbiting nearby stars, including Alpha Centauri. Later, in the 19th century, the progress of spectroscopic techniques allowed scientists to analyze starlight in new ways, revealing the chemical compositions of stars and hinting at the potential for planets beyond our solar system. But it was in the 20th century that Alpha Centauri truly captured the imagination of the scientific community and the public. With the advent of more powerful telescopes and the development of astrophysics, astronomers began to realize that stars like Alpha Centauri are not just distant points of light, but complex systems, possibly hosting planets and other cosmic phenomena. The idea that worlds might exist orbiting our nearest stellar neighbor sparked dreams of future exploration and even the possibility of finding life beyond Earth. Throughout the 20th century, Alpha Centauri served as a crucial reference point in the search for extraterrestrial life. The concept of habitable zones, regions around stars where conditions might support life, became central to the quest for exoplanets. Alpha Centauri, with its proximity and similarity to our Sun, became a natural candidate for targeted searches. Many aspiring astronomers and space agencies considered it a prime candidate for future missions, fueling the hope that one day we might send probes or even humans to explore these neighboring worlds. In recent decades, advances in technology have transformed this dream into a tangible pursuit. The launch of dedicated space telescopes, such as the James Webb Space Telescope, has allowed scientists to peer deeper and with greater clarity into the Alpha Centauri system. These observations have begun to shed light on the complexities of the stars and the potential worlds that may orbit them. Each new discovery in this nearby stellar system carries the weight of centuries of curiosity and the promise of uncovering secrets that could redefine our understanding of the universe. Alpha Centauri's significance in astronomy is woven into the very fabric of our quest to explore the cosmos. It symbolizes both the limits of our knowledge and the boundless horizon of discovery. From ancient stargazers to modern scientists wielding the most advanced instruments, the story of Alpha Centauri is a testament to humanity's enduring desire to understand our place among the stars. And as the James Webb Space Telescope continues to unveil new mysteries in this nearby system, the legacy of Alpha Centauri as a cornerstone of astronomical exploration remains as vibrant as ever. The Alpha Centauri system is a jewel in the night sky, shining brightly as our closest stellar neighbor. To the naked eye, it appears as a single point of light, but through the lens of advanced telescopes, it reveals a fascinating dance of stars, each with its own story to tell. At the heart of this system are three main stars, each playing a unique role in the cosmic ballet that has captivated astronomers for generations. The first of these is Alpha Centauri A, a star remarkably similar to our own Sun. It is a yellow-hued star, slightly larger and more luminous than the Sun, shining with a gentle warmth that has drawn curiosity for centuries. Alpha Centauri A's brightness makes it one of the most prominent stars in our sky, and its characteristics make it a prime candidate in the search for worlds beyond our solar system. Scientists have long observed its steady glow, studying its subtle variations and magnetic activity, all in hopes of understanding how stars like our Sun behave and evolve. Accompanying Alpha Centauri A is its close companion, Alpha Centauri B. Slightly smaller and cooler, Alpha Centauri B is an orange-hued star that circles its partner with a gentle, persistent grace. Its orbit around Alpha Centauri A is tight, taking just over 270 years to complete a full revolution. This intimate dance creates a dynamic environment where the stars influence each other's atmospheres and potential planetary systems. Alpha Centauri B's steadiness and proximity make it a compelling target for studying the conditions that might support life. Completing the trio is Proxima Centauri, the smallest and faintest of the three. Despite its modest brightness, Proxima Centauri holds a special place in the hearts of astronomers. It is a red dwarf, a type of star that is common throughout our galaxy, but often overlooked because of its dim glow. Yet Proxima Centauri is the closest individual star to our Sun, lying just over 4 light-years away. Its proximity has made it a key focus for scientists searching for planets that could harbor life. In recent years, Proxima Centauri has revealed itself as a fascinating cosmic neighbor, with evidence of at least one rocky planet orbiting within its habitable zone, a region where conditions might be just right for liquid water to exist. Each of these stars brings its own set of characteristics that shape the environment of the Alpha Centauri system. Alpha Centauri A, with its brightness and similarity to the Sun, offers a glimpse into what our solar system might have looked like in its youth. Its energetic surface and magnetic activity serve as a natural laboratory for understanding stellar behavior. Alpha Centauri B, with its cooler temperature and closer orbit, adds a layer of complexity, influencing the potential habitability of nearby planets through its radiation and stellar winds. Proxima Centauri, though smaller and less luminous, is perhaps the most intriguing. Its volatile stellar activity, characterized by powerful flares and bursts of radiation, poses challenges for planetary habitability. Yet it also offers invaluable insights into the lives of red dwarf stars, which make up the majority of stars in our galaxy. The discovery of planets orbiting Proxima Centauri has ignited hopes that worlds similar to Earth might exist even around these seemingly modest stars. The combined light and gravitational influence of these three stars create a complex environment where planets could form and evolve in unique ways. The gravitational tug of Alpha Centauri A and B can shape the orbits of planets, influencing their climate and stability over millions of years. Meanwhile, the proximity of Proxima Centauri offers a tantalizing possibility of life-bearing worlds lurking in its shadow, waiting to be uncovered by future missions. As our understanding deepens, aided by powerful telescopes and space observatories like the James Webb Space Telescope, we begin to see the true nature of these stars. They are not just points of light in the sky, but dynamic, evolving spheres of plasma with stories etched into their light. The secrets they hold about stellar life cycles, planetary formation, and potential habitability are opening new chapters in our cosmic journey. In this grand tapestry, the stars of Alpha Centauri remind us that even our closest neighbors are vast, complex worlds waiting to reveal their mysteries. Their characteristics and behaviors serve as a mirror to our own Sun, and perhaps someday soon, they might even reveal signs of life beyond our own planet. As we continue to explore these stellar companions, each discovery brings us closer to understanding our place in the universe and the endless possibilities that lie among the stars. Alpha Centauri stands out as one of the most captivating neighborhoods in our cosmic backyard. Imagine a neighborhood so close that it takes just over 4 years for light to travel from there to here. That's what makes Alpha Centauri not just a point of curiosity, but a prime target for astronomers searching for new worlds beyond our own. It's like having a neighbor right next door, always within reach, yet still full of mysteries waiting to be uncovered. What makes Alpha Centauri so appealing is its proximity. When scientists point their telescopes toward the sky, they often look for stars that are close enough to study in detail. Alpha Centauri, being our nearest stellar neighbor, provides a rare and valuable opportunity. Close proximity means less distance for signals and light to travel, which allows for sharper, more detailed observations. This is especially important when it comes to hunting for planets around other stars. The closer the star, the easier it becomes to detect the tiny gravitational tugs and faint signals that hint at planets orbiting there. Another reason Alpha Centauri captures the imagination is its stellar composition. The system is made up of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are similar to our Sun in size and brightness, which makes them intriguing candidates for hosting planets that could potentially support life. Proxima Centauri, the smallest of the 3, is a red dwarf, cooler and dimmer, but still a fascinating place to look for planets because red dwarfs are the most common type of star in our galaxy. Scientists are particularly excited about Proxima Centauri because it's known to host at least one planet, Proxima Centauri B, that orbits within what is called the habitable zone. This is the region around a star where conditions might be just right for liquid water to exist, a key ingredient for life as we understand it. The possibility that a planet in this zone could support life makes the system even more compelling. Alpha Centauri also offers a perfect laboratory for studying how planetary systems form and evolve. Because the stars are so close together, scientists can compare their properties and learn how similar or different their planetary neighborhoods might be. This helps us understand whether planets like Earth are common or rare in our galaxy. In essence, Alpha Centauri is a cosmic treasure chest, close enough to examine in detail, diverse enough to teach us about the many ways planets can form, and exciting enough to keep hope alive that somewhere out there, perhaps even in this nearby system, we might find signs that life exists beyond our planet. That's why it remains one of the most sought-after targets in our ongoing quest to uncover the secrets of the universe. Over the years, the Alpha Centauri system has captivated astronomers and dreamers alike. Its proximity to Earth makes it an ideal cosmic neighbor, and centuries ago ancient civilizations gazed up at the night sky, wondering about the mysteries that lay beyond. As telescopic technology advanced, the first glimpses of this stellar trio revealed a fascinating and complex neighborhood. Early observations identified Alpha Centauri as a bright and seemingly familiar star, but what truly excited scientists was the realization that it was not just a single star, but a system of 3: Alpha Centauri A, the larger and more luminous star, Alpha Centauri B, slightly smaller and cooler, and the faint red dwarf known as Proxima Centauri, the closest of the 3 to our own solar system. In the latter half of the 20th century, astronomers turned their attention to hunting for planets orbiting these stars. It was a challenging task, given the brightness and closeness of the stars, but persistent efforts paid off. The breakthrough came when astronomers detected signs of a planet around Proxima Centauri, the smallest and faintest of the trio. This planet, Proxima Centauri B, was a rocky world just a little larger than Earth, orbiting within what scientists call the habitable zone, the region where conditions might allow liquid water to exist. The discovery of Proxima Centauri B sent ripples through the scientific community, fueling hopes that this neighboring world could harbor life. Beyond the detection of planets, observations of the stars themselves revealed intriguing details. Scientists noted that Alpha Centauri A and B exhibited slight variations in brightness, hinting at stellar activity and magnetic cycles similar to our Sun. These fluctuations raised questions about the stability of potential planetary environments and the influence of stellar behavior on habitability. Advanced telescopes and spectroscopic studies also uncovered the composition of the stars' atmospheres, providing insights into their chemical makeup and age, which in turn informed theories about the formation and evolution of their planetary systems. The Alpha Centauri system has also played a role in the search for cosmic signals. Over the decades, there have been numerous claims and investigations into possible extraterrestrial communications, some fleeting signals, some unexplained anomalies. While none have been conclusively linked to intelligent life, these tantalizing hints have kept the system at the forefront of the search for extraterrestrial intelligence. All these discoveries, from planets to stellar activity and mysterious signals, have painted a picture of a dynamic and intriguing neighboring system. Each new piece of information has helped scientists understand the delicate dance of stars and planets in this nearby stellar neighborhood. And now, with the advent of the James Webb Space Telescope, the eyes of humanity are poised to unlock even deeper secrets. This powerful observatory promises to shed light on the hidden worlds and unseen phenomena lurking in the shadows of Alpha Centauri, potentially rewriting what we know about our closest cosmic companions. The James Webb Space Telescope stands out as a marvel of modern science and engineering, uniquely equipped to explore the mysteries of nearby stars like Alpha Centauri. Its design and capabilities are tailored to unlock secrets that have eluded astronomers for decades, and its features make it particularly well suited for studying these stellar neighbors. One of the most striking features of the James Webb Space Telescope is its incredible sensitivity. Unlike earlier telescopes, which could be limited by Earth's atmosphere or smaller mirrors, this space-based observatory is built to detect faint signals from distant worlds. Its primary mirror, which measures about 6.5 meters across, is composed of numerous individual segments, carefully aligned to form a giant, precise surface. This expansive mirror gathers light with remarkable efficiency, allowing scientists to observe objects that emit very little light or are buried deep in cosmic dust. When it comes to studying Alpha Centauri, this sensitivity means the telescope can capture detailed images and spectra of the star and its potential planets, even if their signals are faint or obscured. Another key feature is the telescope's advanced suite of instruments designed for a broad range of observations. The James Webb Space Telescope includes cameras capable of capturing images in the near-infrared and mid-infrared wavelengths. Infrared light is especially important because it can penetrate dust clouds that often obscure stellar environments. Many of the planets orbiting stars like Alpha Centauri are hidden behind dust or are in regions where visible light is blocked. By observing in infrared, the telescope can peer through these cosmic veils and reveal planets, atmospheres, and other features that might be invisible to telescopes working only in visible light. The telescope's ability to analyze spectra is another crucial aspect. Spectroscopy involves splitting light into its component wavelengths, much like a rainbow, to study the chemical composition, temperature, and other properties of celestial objects. The James Webb Space Telescope's spectroscopic instruments can detect the faint signatures of molecules in exoplanet atmospheres. This capability is vital for searching for signs of habitability or even life, as the presence of water vapor, methane, or oxygen could hint at biological activity. When studying Alpha Centauri, which is relatively close in cosmic terms, this spectral analysis might reveal the atmospheric makeup of orbiting planets, helping scientists assess whether these worlds could support life. Furthermore, the telescope's position in space offers a significant advantage over ground-based observatories. Operating far beyond the Earth's atmosphere means it does not suffer from atmospheric distortion or weather-related disruptions. This stability allows for extremely precise measurements and high-resolution imaging. For Alpha Centauri, this means astronomers can obtain clearer, sharper images than ever before, resolving details that might be indistinct from the ground. This clarity is essential when trying to distinguish between the star's light and that of nearby planets or other features. The thermal management systems of the James Webb Space Telescope are also vital. It is equipped with a sophisticated sun shield the size of a tennis court, which shields the instruments from the sun's heat and light. This allows the telescope to operate at extremely cold temperatures, below -270 degrees Celsius, which is necessary for infrared observations. Such cold temperatures reduce thermal noise, enhancing the sensitivity and accuracy of the instruments. For studying Alpha Centauri, this means the telescope can detect even the faintest thermal emissions from planets and their atmospheres, providing vital clues about their composition and potential habitability. Finally, the telescope's advanced pointing and stability systems ensure that its observations are incredibly precise. It can lock onto a target and track it with remarkable accuracy, maintaining stable images over long periods. This stability is crucial for studying stars like Alpha Centauri, where tiny fluctuations in light can reveal the presence of orbiting planets or atmospheric phenomena. The ability to hold a target steady for extended observations allows astronomers to gather detailed data and make more accurate assessments of what lies around our nearest stellar neighbor. In summary, the James Webb Space Telescope's unparalleled sensitivity, broad infrared detection capabilities, spectroscopic tools, space-based vantage point, advanced thermal management, and precise pointing systems all combine to make it an exceptional instrument for studying Alpha Centauri. With these features, it is poised to deepen our understanding of these nearby stars and their planetary systems, bringing us closer than ever to answering the age-old question of whether we are alone in the universe. Imagine a telescope so powerful that it can see through the cosmic fog, revealing secrets hidden deep within the universe's most veiled regions. That's the magic of the James Webb Space Telescope's infrared technology. This advanced instrument doesn't just see what the human eye can detect. It peels back layers of cosmic dust and gas, allowing us to observe worlds and phenomena that would otherwise remain cloaked in mystery. At the heart of this capability is the telescope's ability to detect infrared light, a type of electromagnetic radiation with a wavelength longer than visible light, but shorter than microwave radiation. While our eyes are tuned to see the colors of the rainbow, infrared light is invisible to us. However, many fascinating objects in space emit their energy predominantly in these longer wavelengths. For example, young stars often form deep inside thick clouds of gas and dust that block visible light. But these embryonic stars and their surrounding planetary nurseries glow brightly in the infrared. By capturing this glow, the James Webb Space Telescope can peer into these hidden regions, unveiling the earliest stages of star and planet formation. Why is this infrared vision so important? Because the universe is a largely obscured and dusty place. When stars and planets are born, their light often gets trapped within dense clouds of gas and dust. Visible light struggles to escape these cocoons, leaving many cosmic mysteries concealed from traditional telescopes. Infrared light, however, can penetrate these dusty shrouds, acting as a cosmic flashlight that illuminates what's usually hidden from view. This allows scientists to study the birthplaces of stars and planets, and to better understand how planetary systems like our own come into existence. Furthermore, the James Webb Space Telescope's infrared eyes are essential for studying objects that are very far away and therefore very old. As light travels across the vast expanse of space, it takes time to reach us. The farther away an object is, the more its light has been stretched out by the expansion of the universe. This stretching shifts the light towards longer infrared wavelengths. By observing in the infrared, the James Webb Space Telescope effectively looks back in time, seeing galaxies and stars as they were billions of years ago. This gives us a glimpse into the universe's infancy and its evolution over cosmic history. Infrared technology also allows the telescope to analyze the composition of distant planets and their atmospheres. When light from a star passes through a planet's atmosphere, certain molecules absorb specific wavelengths of infrared radiation. These absorption patterns create a spectral fingerprint that reveals the presence of gases like water vapor, methane, or carbon dioxide. Understanding these chemical signatures helps scientists determine whether a planet might be hospitable for life, or if it bears the mark of biological activity. All of this is made possible because of the James Webb Space Telescope's sophisticated infrared instruments. These detectors are cooled to extremely low temperatures to reduce thermal noise, unwanted heat signals that could drown out the faint infrared signals from distant objects. This thermal management is crucial for achieving the sensitivity needed to detect the faintest signals. Additionally, the telescope's stable, space-based position minimizes vibrations and temperature fluctuations, ensuring that its observations remain precise and clear. In essence, the infrared technology of the James Webb Space Telescope acts as a cosmic microscope, allowing us to see through the universe's dusty veil and uncover its deepest secrets. It opens a window into the birthplaces of stars and planets, the evolution of galaxies, and perhaps even the signatures of life beyond our world. With this extraordinary tool, we stand on the brink of discoveries that could transform our understanding of the universe and our place within it. The James Webb Space Telescope is equipped with a suite of advanced instruments that work together to deepen our understanding of stars and their surrounding planets. Each instrument has a specific role, carefully designed to capture different aspects of the universe, especially in the infrared part of the spectrum, where much of the universe's hidden secrets reside. One of the primary instruments is the near-infrared camera, often called the near-infrared camera. It is a versatile tool that captures images of stars, galaxies, and planets in the near-infrared wavelengths. Because it observes in this part of the spectrum, It can see through cosmic dust clouds that often obscure objects when viewed in visible light. This ability makes it invaluable for studying star formation regions and spotting young planets still shrouded in their natal dust. The near-infrared camera also helps identify faint objects near bright stars, which is essential when searching for planets orbiting distant stars. Complementing this is the near-infrared spectrograph. This instrument breaks down light into its component wavelengths, much like a prism creates a rainbow from sunlight. By analyzing the spectrum of light from stars and planets, scientists can determine what they are made of, how they are moving, and whether they hold atmospheres that might support life. For exoplanet studies, this spectrograph can detect tiny changes in the starlight as planets pass in front of their host stars, revealing clues about their atmospheric composition and even weather patterns. Moving to the mid-infrared part of the spectrum, the mid-infrared instrument takes center stage. This instrument is crucial for studying the thermal emission from planets, stars, and dust clouds. It can detect the heat coming from objects that are too faint to see with other instruments, allowing scientists to study the temperature and composition of exoplanet atmospheres in detail. The mid-infrared instrument also helps unravel the mysteries of planetary formation, revealing how planets develop and evolve over time. Another key component is the fine guidance sensor and the near-infrared imager and slitless spectrograph. While primarily responsible for keeping the telescope precisely pointed at its targets, the fine guidance sensor also provides valuable data for high-precision measurements and observations. The near-infrared imager and slitless spectrograph, which can operate both as an imager and a spectrograph, expands the telescope's capacity to study objects in various ways, whether capturing sharp images or analyzing the light spectrum without needing to position a slit over the target. Together, these instruments enable the James Webb Space Telescope to observe the universe in extraordinary detail. They allow scientists to peer through cosmic dust, analyze the atmospheres of distant worlds, and uncover clues about how stars and planets form and evolve. With each observation, these tools bring us closer to answering some of the biggest questions about the universe and our place within it. The synergy of these instruments promises new discoveries that could reshape our understanding of the cosmos for generations to come. While the James Webb Space Telescope is a marvel of modern engineering and a powerful tool for exploring the universe, it does face a number of limitations and challenges that can influence its observations. Understanding these hurdles helps us appreciate the delicate balance of technology, physics, and celestial phenomena involved in unlocking the secrets of distant worlds. One of the primary challenges lies in the telescope's sensitivity to its environment. Although it is designed to operate in the cold vacuum of space, it still requires extremely precise thermal management. The telescope's instruments must be kept at incredibly low temperatures to detect faint infrared signals from distant stars and planets. Even tiny fluctuations in temperature can cause noise and distortions, making it difficult to discern subtle signals. This means that engineers had to develop elaborate cooling systems and careful thermal shielding to prevent heat from the telescope itself from contaminating its observations. Another significant obstacle is the interference caused by cosmic dust and gas. While the James Webb Space Telescope is equipped with infrared capabilities to peer through dust clouds, these same particles can sometimes obscure or scatter the signals it aims to capture. Regions of space rich in dust and gas are often the most interesting for studying star and planet formation, but they can also pose obstacles by dimming or distorting the light that reaches the telescope's sensors. This means that scientists must carefully analyze data to distinguish genuine signals from noise created by cosmic material. The telescope's position in space, although advantageous compared to ground-based observatories, also presents logistical and technical challenges. The James Webb Space Telescope is parked at a stable point known as the second Lagrange point, which is millions of miles away from Earth. While this vantage point allows for an unobstructed view of the cosmos, it also means that any repairs or adjustments cannot be made easily. If a critical component were to malfunction, fixing it would be impossible without the aid of spacecraft or future missions, making the initial design and reliability of the instruments all the more crucial. Another issue is the finite lifespan of the telescope's instruments. Over time, exposure to cosmic radiation and the harsh environment of space can degrade sensors and other components. This limits the duration over which the James Webb Space Telescope can continue to provide high-quality data. Planning for these eventualities involves meticulous calibration and maintenance of the instruments, and it underscores the importance of maximizing the scientific return within the telescope's operational lifetime. Lastly, the sheer volume of data generated by the James Webb Space Telescope presents its own challenge. The telescope produces vast amounts of information that must be transmitted back to Earth, processed and analyzed. This requires sophisticated data management, storage, and computational resources, along with international collaboration among scientists and researchers. Managing this data flow efficiently is essential to ensure that groundbreaking discoveries are promptly identified and understood. In essence, while the James Webb Space Telescope stands at the forefront of space exploration, it must contend with thermal, environmental, logistical, and technical hurdles. Overcoming these challenges demands ingenuity, precision engineering, and careful planning, all of which are vital as we push the boundaries of our knowledge and seek to uncover the universe's deepest secrets. Last month, the scientific community buzzed with excitement and a touch of concern when the James Webb Space Telescope turned its enormous, sophisticated instruments towards the star system known as Alpha Centauri. This star system, the closest to our own solar system, has long been a tantalizing target for astronomers eager to uncover the secrets of neighboring worlds. But what the Space Telescope revealed this time was far more intricate and intriguing than anyone had anticipated. The moment the data arrived, it sparked a whirlwind of curiosity and questions. The telescope's sensors detected something unusual around a planet orbiting Alpha Centauri A, the brighter and more massive of the two main stars in the system. It was a faint yet distinct signal that hinted at the presence of a phenomenon or object that scientists hadn't expected to find so close to such a familiar star. Initially, the team at the space agency believed it might be a simple case of interference or some cosmic debris floating in the vastness of space. After all, the universe is filled with countless particles, dust, and even stray light from distant stars that can sometimes mimic signals of interest. Yet, as the data was analyzed further, a different story began to emerge, one that sparked both excitement and cautious skepticism. The signal itself appeared to be a pattern of faint light fluctuations, not unlike a flickering beacon, but with a repeating rhythm that suggested it was not just random cosmic noise. The observations indicated that this pattern persisted over multiple days, which made the team sit up and re-examine their assumptions. Could this be an artifact of the telescope's sensors, or was it a genuine sign of something extraordinary happening in that distant star system? What made the discovery even more perplexing was the nature of the pattern. It seemed to be a series of brief flashes, almost like a heartbeat, occurring at regular intervals. This rhythmic flickering raised a host of questions. Was it a natural phenomenon, perhaps some kind of stellar activity or atmospheric disturbance on the planet? Or could it be something far more extraordinary, an artificial signal, perhaps emanating from an advanced civilization or a probe of some sort? The team quickly mobilized their resources to verify the observation. They cross-checked the data with other instruments and looked for similar signals in the neighboring regions of space. To their surprise, the pattern persisted across multiple observations, and no natural explanation seemed to fit the data neatly. They even considered whether the signal could be a signature of some kind of technological activity, perhaps a beacon or a communication signal. This prompted a wave of intense discussions among scientists around the world. Some were cautious, urging patience and further verification. Others speculated wildly about the implications of discovering signs of intelligent life so close to humanity's reach. The questions multiplied. Was this a sign of a civilization that had mastered space travel? Could it be evidence of a new kind of natural phenomenon that we simply hadn't seen before? Or was it an anomaly caused by the complex environment around Alpha Centauri A? Throughout this process, the engineers and scientists working with the James Webb Space Telescope faced their own set of challenges. The delicate instruments had to be calibrated with extraordinary precision to ensure that the signals weren't artifacts of the equipment itself. Managing the vast amount of data streaming in from this distant corner of the universe was a feat in itself. Every byte of information had to be meticulously analyzed, filtered and cross-verified to avoid false alarms. Meanwhile, the environmental conditions around the telescope posed their own hurdles. The Space Telescope operates in the cold vacuum of space, and even tiny vibrations or temperature fluctuations can affect the delicate sensors. The mission teams had to carefully rule out all possible sources of interference, both from the telescope and from the cosmic environment, to be confident that what they were seeing was real. The more they looked, the more the mystery deepened. The pattern of flickering did not match any known natural phenomena such as solar flares, stellar pulsations, or planetary atmospheric effects. This only heightened the curiosity. It was as if the universe was whispering a secret, one that might require new theories or even new physics to fully understand. Scientists emphasized that extraordinary claims would require extraordinary evidence. They planned to continue observing the system with even greater detail, hoping to catch the signal again and perhaps even detect its source more precisely. If real, this discovery could be a groundbreaking milestone, potentially opening a new chapter in our understanding of the universe and our place within it. In the end, the observation around Alpha Centauri A served as a powerful reminder of both the promise and the peril of exploring the unknown. The James Webb Space Telescope had once again demonstrated its remarkable capability to peer into the depths of space and uncover phenomena that challenge our understanding. But it also underscored the necessity of patience, rigorous analysis, and cautious optimism in the pursuit of cosmic truths. Whatever this flickering signal truly signifies, it has already ignited a new wave of curiosity and hope that humanity's quest for knowledge is far from over. In the vast, silent depths of space, sometimes a signal emerges that makes scientists sit up and take notice, and the recent discoveries near Alpha Centauri have done just that. The James Webb Space Telescope, with its extraordinary sensitivity and cutting-edge technology, peered into the star system's distant neighborhood and detected something truly extraordinary, an unusual rhythmic flickering signal that defied easy explanation. This signal was unlike anything astronomers had expected to see. It wasn't a steady flicker or a simple burst of light. Rather, it was a highly regular repeating pattern, like a heartbeat echoing across the cosmic void. The flickering appeared at consistent intervals, almost as if it were a deliberate message or a natural phenomenon with a rhythm of its own. Its frequency, or how often the pattern repeated, was precise and unwavering over the course of many observations. Such regularity is rare in natural celestial phenomena, which tend to be more chaotic and unpredictable. The signal's characteristics immediately sparked curiosity and speculation. Some scientists wondered if it might be an echo of an artificial source, perhaps a sign of advanced extraterrestrial technology. Others considered natural explanations, pondering whether this could be a natural but unknown phenomenon, perhaps a new kind of stellar activity or a mysterious natural process that we had yet to understand. The truth was, the signal was unlike any known natural emission or fluctuation observed before in the star system. What made this discovery even more intriguing was its location. Alpha Centauri, our nearest star system, has long been a focus of scientific curiosity because of its proximity and similarity to our own Sun. The idea that a signal of such unusual nature could originate from a system so close to Earth stirred the imaginations of scientists and the public alike. If this flickering was artificial, it could be a hint of an intelligent civilization, or at least an artifact of some unknown technology lurking in the star's vicinity. Scientists took great care in examining the data to rule out other explanations. Could it be interference from Earth-based sources or satellites? Or perhaps a glitch in the telescope's instruments? After thorough checks, these possibilities were largely eliminated. The signal's distinct pattern persisted across different observations, and its precise rhythm made it unlikely to be a random anomaly or a technical error. It seemed, in the words of some researchers, to be something worth investigating further, a genuine anomaly that challenged current understanding. The detection sparked a flurry of activity across the global scientific community. Teams of astronomers and astrophysicists scrambled to analyze the signal from every angle, trying to decipher whether it was a message, a natural phenomenon, or an entirely new kind of cosmic event. Some suggested that the signal might be a form of communication, perhaps a beacon or a form of electromagnetic signature meant for distant observers. Others remained cautious, emphasizing the importance of corroborating the findings with additional observations and data. As the data poured in, theories multiplied. Could the flickering be related to a pulsar, a type of rapidly rotating neutron star known for emitting regular signals? Or might it be a natural but still unknown stellar activity, something that mimics artificial signals? The uncertainty only added to the mystery, fueling both scientific debate and public fascination. Many wondered if this could be the first real hint of extraterrestrial intelligence, a message waiting to be deciphered. The James Webb Space Telescope's ability to detect such subtle signals marks a new era in the search for life beyond Earth. Its extraordinary sensitivity allows it to pick up faint periodic signals that might have gone unnoticed with earlier instruments. This detection underscores the importance of exploring nearby star systems with the most advanced tools available, as the universe continues to surprise us with phenomena that challenge our understanding and ignite our imagination. In the days and weeks that followed, scientists remained vigilant. They planned additional observations, hoping to confirm the signal's persistence and to gather more data that could shed light on its origin. The possibility that we might be on the cusp of discovering something truly groundbreaking, whether an unknown natural phenomenon or evidence of extraterrestrial technology, made this a moment of profound scientific promise. Whatever the ultimate answer, the flickering signal near Alpha Centauri has opened a new chapter in our quest to understand the cosmos, a reminder that even in the silence of space, there are whispers waiting to be heard. The recent discoveries near Alpha Centauri have sent ripples of excitement through the scientific community and the wider world alike. For decades, astronomers and astrophysicists have developed models and expectations based on what we knew, or thought we knew, about this neighboring star system. These models painted a picture of a relatively quiet, familiar stellar environment, with planets that might harbor conditions suitable for life, but nothing extraordinary beyond the usual cosmic phenomena. When the James Webb Space Telescope first pointed its highly sensitive instruments toward Alpha Centauri, the anticipation was that it would uncover more about the planets orbiting this star, perhaps identifying atmospheric compositions, surface conditions, or signs of habitability. Instead, what it detected was something entirely unexpected. A rhythmic flickering signal, highly regular and repeating with astonishing consistency, appeared near Alpha Centauri A. This was not the kind of data scientists had predicted, or even considered as a possibility. Prior expectations for signals like these were mostly rooted in natural astrophysical phenomena. Astronomers often look for irregular bursts of light or radio waves that can be explained by known cosmic events, pulsars, quasars, or stellar activity. But a signal that repeats with such precision and regularity defies typical natural explanations. It was as if someone or something was intentionally sending a message, or perhaps a natural process we have yet to understand was producing a perfectly ordered pattern. This discovery challenged the existing models in significant ways. For one, the notion that such a signal could originate from natural causes was suddenly less convincing. Traditionally, scientists believed that natural signals, especially those that are rhythmic or repeating, would exhibit some variation or irregularity due to the chaotic and dynamic nature of cosmic phenomena. The extraordinary regularity of this signal suggested a level of precision that seemed more aligned with intelligent engineering than natural processes. Furthermore, the previous expectation that the star system would be relatively inactive in terms of electromagnetic interference or artificial signals was upended. The models had predicted a relatively stable environment, devoid of any clear signs of technological activity. Instead, the data hinted at a potential artificial origin, sparking debates about whether this could be an extraterrestrial communication or some unknown natural phenomenon mimicking artificial signals. Scientists are now re-evaluating their understanding of stellar environments and the potential for life beyond Earth. They are considering the possibility that this signal might be a form of communication or a marker left by an advanced civilization. The findings are compelling enough to suggest that the universe may be more interconnected and more complex than previously imagined. It is a reminder that our models, while useful, are still limited by the scope of human knowledge and the assumptions we have held for decades. The comparison between this recent discovery and earlier expectations highlights a fundamental shift in cosmic exploration. Before, the search for extraterrestrial intelligence was based on the assumption that if signals from other civilizations existed, they would be sporadic or faint. easily missed or dismissed as natural noise. Now, the very clarity and regularity of the signal challenge that notion. It prompts scientists to refine their models, to consider new possibilities, and to expand their understanding of what natural or artificial phenomena might look like across the universe. In essence, the findings near Alpha Centauri have turned some of our most cherished ideas on their heads. They encourage a sense of wonder and curiosity, reminding us that the cosmos still holds many surprises. As scientists continue to analyze this remarkable signal, they are also revisiting their expectations, pushing the boundaries of what we believe is possible in the universe and opening new doors to understanding the mysteries that lie beyond our home planet. Recent observations near Alpha Centauri have stirred a wave of excitement and curiosity within the scientific community. The James Webb Space Telescope, with its unprecedented sensitivity and precision, detected a highly regular and repeating flickering signal emanating from the vicinity of the star system. At first glance, such a signal might seem like a mere natural rhythm, perhaps caused by stellar activity or cosmic phenomena. However, the extraordinary nature of this pattern has led many to consider the possibility of something far more intriguing, the potential of technological activity beyond our world. The signal's extraordinary regularity sets it apart from the typical cosmic noise that usually fills the universe. Natural phenomena such as pulsating stars or cosmic dust tend to produce signals that fluctuate irregularly or fade into background noise. But what the James Webb Space Telescope detected was a steady, rhythmic flickering, repeating with a precision that suggests an intentional design rather than randomness. This kind of pattern is reminiscent of signals crafted by intelligent beings, much like the signals humans have sent into space in hopes of reaching extraterrestrial civilizations. Scientists have examined various explanations for this phenomenon. Natural causes such as unusual stellar behavior or interstellar material have been considered and largely ruled out due to the signal's remarkable consistency. The possibility of it being an artifact of the telescope itself has also been carefully scrutinized and dismissed after rigorous checks. The leading hypothesis, therefore, points toward an artificial origin, possibly a form of communication or a technological beacon. This idea, while still speculative, has ignited a surge of interest and debate around the world. The notion that we might be witnessing a sign of technological activity from an alien civilization is both exhilarating and daunting. Such a discovery would represent a momentous leap in our understanding of the universe and our place within it. It could suggest that intelligent life exists elsewhere and has developed the means to communicate across the vast distances of space. Alternatively, some scientists ponder whether the signal might be from an unknown natural phenomenon that mimics artificial signals, challenging our current models of stellar environments. As researchers continue to analyze the data, the global community remains both cautious and hopeful. They recognize that extraordinary claims require extraordinary evidence. Still, the consistency and clarity of the signal make it a compelling focus for ongoing investigation. The possibility of discovering an extraterrestrial message or an uncharted cosmic phenomenon has energized scientists, inspiring new missions and technological innovations aimed at unraveling this cosmic mystery. In the end, what makes this discovery so compelling is not just the potential for contact or understanding, but also the profound questions it raises about the universe and our place within it. Are we truly alone, or is this flickering beacon a sign of distant civilizations reaching out across the stars? The answers are still out there, hidden among the cosmic signals that the James Webb Space Telescope continues to uncover, promising a new era of discovery and wonder. As scientists pore over the data, trying to make sense of these unusual signals, many questions come to mind. What could be causing these strange phenomena? Are they signs of something entirely new in the universe? Or could they be explained by more familiar natural processes? The possibilities are as varied as the cosmos itself, and each one invites a different kind of curiosity and investigation. One of the first ideas that comes to mind is that these signals might be the result of natural cosmic phenomena. For instance, some of the signals could originate from distant stars or galaxies that are behaving in ways we have not yet fully understood. The universe is filled with energetic events, flaring stars, supermassive black holes, or pulsating neutron stars, that can produce powerful bursts of radiation. Sometimes these natural phenomena create signals that, when observed from Earth or from our space telescopes, appear unusual or unexpected. In these cases, what seems like an anomaly might simply be a new type of cosmic activity that scientists have not previously detected. Another possibility relates to the way light and other signals travel across vast stretches of space. Sometimes, signals can be distorted or affected by the interstellar medium, the clouds of gas and dust that fill the space between stars. These interstellar clouds can scatter, absorb, or even amplify signals in ways that make them seem strange or out of place. For example, a signal might appear to flicker or change in intensity as it passes through these cosmic particles, creating an illusion of something extraordinary when, in fact, it is a natural consequence of the journey through space. Yet another explanation involves the phenomenon of cosmic coincidence. The universe is enormous, and the odds of certain signals appearing to be meaningful or intentional might simply be the result of chance. Sometimes, signals from distant sources could be misunderstood because we are seeing them in a particular moment, or because they are being misinterpreted by our instruments. In the realm of astronomy, where signals can be faint and fleeting, it is not uncommon for scientists to initially think they have uncovered something extraordinary, only to realize later that it was a natural, albeit rare, event. Beyond natural causes, some scientists consider that these signals could be the remnants of artificial sources, technological civilizations perhaps existing on planets orbiting distant stars. If that were the case, it would represent one of the most profound discoveries in human history. These signals could be intentional messages, crafted to communicate across light years, or they might be accidental emissions from alien technology. In some cases, the signals might resemble what we would expect from intelligent life: patterns that repeat or encode information, or signals that show signs of deliberate modulation. However, it is crucial to approach these interpretations with caution. The history of astronomy is filled with examples of signals initially thought to be signs of extraterrestrial intelligence, only to be later explained by more mundane causes. For instance, some signals have turned out to be interference from human-made satellites or terrestrial radio sources. This reminds us that before jumping to extraordinary conclusions, scientists exhaust all possibilities of natural or technical origins. Another intriguing, though less likely explanation involves the concept of unknown physics, phenomena that challenge our current understanding of the universe. Sometimes, signals might hint at new physical principles or particles that have yet to be discovered. Such discoveries could revolutionize physics and cosmology, revealing that the universe is even more mysterious and complex than we currently imagine. In considering all these possibilities, it becomes clear that interpreting these signals requires a careful, methodical approach. Scientists must sift through vast amounts of data, cross-check findings, and consider every natural and artificial explanation. They look for patterns, repetitions, and anomalies, trying to distinguish between what might be a cosmic coincidence and what could be a genuine sign of something extraordinary. Ultimately, whether these signals are caused by natural cosmic phenomena, artificial sources, or even unknown physics, each explanation opens a new window into understanding the universe. Whatever the true origin, these mysteries remind us of how much there is still to learn. They push the boundaries of human knowledge and spark our imagination, fueling the hope that someday we might uncover answers that change our view of the universe and ourselves forever. As we stand on the brink of these extraordinary discoveries, one question looms large in the minds of scientists and curious minds alike. Could these signals, so mysterious and compelling, be evidence of extraterrestrial life or advanced technology from beyond our planet? It's a question that ignites both hope and caution, weaving together our deepest longing to connect with others in the universe and our need for rigorous proof before jumping to conclusions. When scientists analyze these cosmic signals, they begin by searching for patterns or structures that seem too deliberate to be random. If a signal contains a repeating pattern or a complex sequence that cannot be easily explained by known natural phenomena, it raises eyebrows and sparks intense interest. Some researchers ponder whether such patterns could be akin to a form of communication, an attempt by intelligent beings to reach out across the vast emptiness of space. Imagine, for a moment, a civilization millions of light years away trying to send a message, carefully crafted to stand out among the noise of the cosmos. It's a tantalizing thought, stirring the imagination and fueling hopes that we are not alone. Yet, scientists are painfully aware of the pitfalls of jumping to conclusions. The universe is a crowded and dynamic place, filled with natural phenomena that can produce signals mimicking artificial origins. Pulsars, rapidly spinning neutron stars emitting beams of radio waves, can create signals that seem patterned but are entirely natural. Likewise, cosmic rays and other energetic processes can generate signals that are difficult to decipher. These natural sources often challenge our ability to tell whether we are witnessing evidence of life or simply the universe doing what it does best, creating complex but natural phenomena. In the pursuit of understanding, researchers also consider the possibility of unknown physics, forces or particles that do not fit within our current scientific framework. Sometimes, signals defy easy explanation, prompting scientists to think outside the box and consider the idea that we might be glimpsing entirely new physics. If such physics exists, it could potentially be harnessed by intelligent civilizations to produce signals or technologies beyond our current comprehension. The search for extraterrestrial intelligence has been a part of scientific inquiry for many decades. Projects like the Search for Extraterrestrial Intelligence involve scanning the cosmos for signals that resemble a form of cosmic Morse code, patterns that stand out from the cosmic background. If a signal were to be confirmed as originating from an intelligent source, it would be one of the most profound discoveries in human history, fundamentally altering our understanding of ourselves and our place in the universe. However, confirming the artificial origin of a signal is an intricate process. Scientists look for consistency, repeatability, and context. They analyze the signal's frequency, modulation, and the environment in which it was detected. They seek corroboration from multiple observatories and independent teams around the world. The process is painstaking, requiring patience, skepticism, and a rigorous approach that leaves no room for error or false alarms. In the end, whether these signals turn out to be evidence of extraterrestrial life or not, their study enriches our understanding of the cosmos. It pushes us to refine our scientific techniques, explore new physics, and expand our knowledge about natural phenomena. It also reminds us of the vastness of the universe and the possibility that we might someday find ourselves in a broader cosmic community. The idea that we might be on the verge of discovering intelligent life beyond Earth is both exhilarating and humbling. It invites us to imagine a universe teeming with other civilizations, each with their own stories, technologies, and ways of understanding reality. Whether or not these signals are truly from extraterrestrial intelligences, the pursuit itself unites us in a common quest, one that spans the stars and reaches into the very depths of our curiosity about existence. As scientists delve into the mysteries revealed by the James Webb Space Telescope, it becomes essential to consider all possible explanations, especially those rooted in natural phenomena. Sometimes what appears to be an unusual signal might have a perfectly natural origin, and understanding these alternatives helps to clarify the true nature of what the telescope is observing. One plausible natural explanation involves cosmic objects emitting signals that, at first glance, seem unusual. For example, pulsars are rapidly spinning neutron stars that send out beams of radio waves like cosmic lighthouses. These beams sweep across space with incredible regularity, and sometimes their signals can appear as strange patterns or bursts that might resemble signs of alien activity. When scientists analyze these signals, they carefully examine their frequency, timing, and polarization to distinguish between what might be a natural pulsar and something potentially artificial. Another natural phenomenon that can mimic unusual signals is the activity within star-forming regions. These stellar nurseries are bustling with energetic processes, massive clouds of gas and dust collapsing under gravity, magnetic fields twisting and snapping, and radiation from young stars piercing through the surrounding material. Occasionally, these turbulent environments produce intense bursts of radio waves or other electromagnetic signals that could be mistaken for signs of intelligence. However, by studying the context and the specific characteristics of these emissions, researchers can often attribute them to natural astrophysical processes. Fast radio bursts present another intriguing natural phenomenon. These are incredibly brief but intense flashes of radio waves originating from distant galaxies. Although their exact origins are still a matter of active research, one leading idea suggests they result from magnetars, highly magnetized neutron stars that undergo sudden energetic outbursts. These bursts are fleeting, yet their complex structures and repetitive patterns can sometimes resemble signals that, without careful analysis, might be misinterpreted as signs of extraterrestrial intelligence. There are also phenomena related to the interactions between particles and magnetic fields in space. For instance, the solar wind, a continuous flow of charged particles from our own sun, can interact with Earth's magnetic field, producing radio emissions known as auroras. While these are well understood in our vicinity, similar processes occurring elsewhere in the universe could generate signals that seem unusual, but are, in fact, natural plasma interactions. Lastly, unknown physics or exotic states of matter might sometimes produce electromagnetic signals that are difficult to categorize. These could involve phenomena like black hole accretion disks or cosmic rays interacting with magnetic fields in ways that produce unique emissions. Although these processes are not fully understood, they remind us that the universe is filled with natural phenomena that are still waiting to be comprehended. In the end, the challenge for scientists is to differentiate between signals caused by natural astrophysical processes and those that might hint at something more extraordinary. By thoroughly investigating these natural explanations, they ensure that any claim of an artificial origin is backed by rigorous evidence. This careful approach maintains the integrity of the search and deepens our understanding of the universe's vast, complex, and wondrous tapestry. When scientists hear a strange signal from the depths of space, their first challenge is to determine whether it's a natural phenomenon or something artificial, perhaps a sign of intelligent life beyond Earth. This process is like detective work, requiring patience, careful analysis, and a deep understanding of the universe's many mysteries. The first step is to scrutinize the signal's characteristics. Natural cosmic events, such as pulsars, which are rapidly spinning neutron stars emitting beams of radio waves, or energetic bursts called fast radio bursts, often produce signals with specific patterns. These patterns tend to repeat in predictable ways or exhibit certain frequency signatures that scientists recognize from previous observations. By comparing the new signal to known natural sources, researchers can identify familiar patterns and rule out natural origins. Scientists also examine the signal's stability and consistency. Natural phenomena often produce signals that vary over time or display a broad range of frequencies. For example, a pulsar's signal might pulse at regular intervals, while a star-forming region might emit diffuse, irregular signals. If a signal is remarkably stable, narrow in frequency, and appears to be intentionally directed or modulated, it becomes more intriguing as a potential artificial source. These clues suggest that the signal might have been designed with a purpose, perhaps to communicate. Another critical aspect is the signal's complexity. Natural signals tend to have certain randomness or noise, reflecting chaotic processes in space. In contrast, artificial signals may have encoded information, deliberate patterns, or mathematical sequences that stand out from the background noise. Scientists look for signs of encoding, repeating patterns, prime numbers, or other mathematical constructs, because these could indicate an intelligent origin. To distinguish artificial signals further, researchers perform multiple rounds of verification. They analyze the signal using different telescopes, and at different times to ensure it's not a transient artifact or interference from Earth-based sources like satellites or radio stations. Cross-checking with other observatories helps confirm the signal's extraterrestrial origin and eliminate terrestrial sources of interference. Additionally, scientists consider the context of the signal. They evaluate whether the source's location corresponds with a known star or galaxy where life might exist. They also assess whether the signal's properties align with what would be expected from natural physics, or if they suggest engineered technology. Throughout this process, scientists maintain a cautious stance. They recognize that many signals initially seem promising, but often turn out to be natural or man-made interference. Yet, even when signals are ultimately explained by natural causes, the investigation enriches our understanding of cosmic phenomena. Each effort refines the tools and knowledge needed to detect genuine signs of extraterrestrial intelligence in the future. In the end, distinguishing natural from artificial signals in space is a meticulous, step-by-step process. It's about listening carefully, analyzing patterns, verifying sources, and keeping an open mind. Every signal, whether natural or artificial, teaches us more about the universe and our place within it. In the vast, shimmering reaches of our neighboring star system, Alpha Centauri, scientists have long wondered about the hidden treasures that might lie beyond the familiar. It isn't just a collection of stars and planets, it's a cosmic tapestry woven with mysteries and rare phenomena that challenge our understanding of what the universe can hold. Among these are objects so uncommon and extraordinary that they seem almost like celestial legends, hypotheses born from the depths of scientific curiosity and the desire to explore the unknown. One of the most intriguing possibilities is the existence of rogue planets. These are worlds that drift through space unbound to any star. Unlike the planets we know orbit stars in predictable paths, rogue planets wander the galaxy alone, cast adrift by gravitational upheavals or violent cosmic events. In the neighborhood of Alpha Centauri, scientists speculate that such planets might exist, hidden in the darkness, their surfaces bathed in cold, unfiltered starlight. Because these planets do not orbit a star, they are incredibly difficult to detect, often revealing their presence only through their gravitational effects on nearby objects or subtle heat signatures. The thought of these solitary worlds sparks wonder. What kind of landscapes might they have? Could some harbour underground oceans warmed by radioactive decay, perhaps offering refuge for some form of life? Another fascinating hypothesis involves the presence of ancient collapsed stellar remnants known as neutron stars. These dense objects are the remnants of stars that have ended their lives in spectacular supernova explosions. Neutron stars are incredibly compact, so dense that a sugar cube-sized amount of their material would weigh as much as a mountain. Though typically found scattered throughout the galaxy, some scientists believe that a neutron star might be lurking near Alpha Centauri, perhaps as part of a binary system or captured by gravitational forces. If such a neutron star were present, it could emit intense beams of radiation called pulsar signals, which can be detected across vast cosmic distances. Finding such a pulsar in our neighboring star system would be a groundbreaking discovery, offering insights into stellar evolution and the extreme physics of matter under extraordinary pressures. Then there are the enigmatic objects known as white dwarfs, remnants of stars that have exhausted their nuclear fuel and shed their outer layers. While white dwarfs are more common throughout the galaxy, the possibility of a nearby, unusually massive or hot white dwarf lurking near Alpha Centauri opens new avenues for scientific exploration. These stellar remnants can sometimes have strong magnetic fields or unusual compositions, making them objects of intense interest. Their presence could influence the gravitational dynamics in the system, and their light emissions might reveal clues about the history of star formation in our cosmic neighborhood. Perhaps most tantalizing are the hypothetical existence of exotic objects such as quark stars or even primordial black holes. Quark stars are theorized to be even denser than neutron stars, composed of quark matter, particles that make up the fundamental building blocks of protons and neutrons. Although their existence remains speculative, discovering such an object near Alpha Centauri would revolutionize our understanding of matter and the fundamental forces of nature. Primordial black holes, on the other hand, are thought to be remnants from the very early universe, formed fractions of a second after the Big Bang. If any such black holes were present in our local cosmic environment, they would be tiny, yet incredibly dense, capable of swallowing matter and light alike. Detecting these would be an extraordinary leap forward in understanding the origins of the universe itself. Beyond these rarities, scientists also consider the potential for artificial structures or artifacts, remnants of an advanced civilization that might have once inhabited the region. While no evidence of such objects has been found so far, the sheer improbability of their existence fuels the imagination. Could there be remnants of megastructures like Dyson spheres, hypothetical constructs designed to harness the energy of a star, or other engineered objects that have somehow survived the ravages of time? In the end, the universe around Alpha Centauri remains a frontier of infinite possibilities. Each hypothesis, each exotic object, pushes the boundaries of our knowledge and inspires us to look deeper into the cosmos. As our telescopes and detection methods grow more sophisticated, the day may come when we uncover these rare celestial wonders, revealing secrets that could reshape our understanding of the universe and perhaps even our place within it. The search continues, driven by curiosity, and a relentless desire to explore the unknown. In recent months, the scientific community has been captivated by astonishing discoveries made by the James Webb Space Telescope. Its observations of distant cosmic regions have revealed phenomena that seem to echo some of the most intriguing hints we've uncovered in Alpha Centauri. These revelations open a window into the universe's most mysterious and exotic objects, stirring imaginations and challenging our understanding of what lies beyond our solar neighborhood. One of the most striking parallels comes from the detection of unusual structures around distant stars, which resemble the kinds of megastructures some scientists have long speculated could exist if advanced civilizations were to harness the power of their stellar environments. These structures appear as irregular dimming patterns in the light emitted by their host stars, much like the mysterious signals and dimming events observed in some stars within Alpha Centauri. While many of these phenomena can be explained by natural causes, such as vast clouds of dust or orbiting debris, the sheer complexity and scale of some of these structures continue to fuel speculation about their origins. Alongside these potential artificial constructs, the James Webb Space Telescope has also identified a variety of exotic celestial objects that mirror the rare objects we consider in Alpha Centauri. For instance, the telescope has spotted neutron stars, dense remnants of collapsed supernovae, whose intense magnetic fields and rapid rotations produce beams of electromagnetic radiation. Some of these neutron stars emit signals that could, in theory, be mistaken for artificial communications if their signals were observed without context. This reminds us how vital it is to distinguish natural astrophysical phenomena from potential signs of extraterrestrial intelligence. Another remarkable discovery involves black holes of the primordial kind. Black holes formed in the universe's earliest moments. These black holes are incredibly small, yet extraordinarily dense, and their gravitational effects can influence the surrounding space in subtle but detectable ways. The James Webb Space Telescope has observed effects akin to those expected from primordial black holes, such as unusual gravitational lensing patterns. These phenomena echo the speculative ideas about primordial black holes in Alpha Centauri, objects that could explain some of the universe's missing mass or act as seeds for larger cosmic structures. White dwarfs, the dense cores left behind after stars exhaust their fuel, have also been observed in greater detail. Some white dwarfs display peculiar atmospheric compositions or emit faint signals that challenge traditional models. These objects, especially when found in binary systems, can exhibit complex interactions, sometimes leading to explosive events. The study of these phenomena sharpens our understanding of stellar evolution and may even hint at processes that could produce signals or structures similar to those we seek in distant star systems. Perhaps most tantalizing are the observations related to quark stars, hypothetical objects even denser than neutron stars, composed entirely of quark matter. Although direct evidence remains elusive, the James Webb Space Telescope's sensitive instruments have detected signals that could be consistent with such exotic objects. If confirmed, these findings could revolutionize our understanding of matter under extreme conditions and provide clues about the universe's fundamental building blocks. All these discoveries underscore a vital point. The universe is a place of endless wonder and complexity. The phenomena observed by the James Webb Space Telescope mirror many of the enigmatic features we suspect exist in Alpha Centauri. Whether it's the potential for artificial megastructures, the presence of exotic stellar remnants, or the mysterious influence of primordial black holes, each new observation brings us closer to comprehending the cosmic tapestry. As our tools and techniques improve, so too does our ability to decipher the universe's deepest secrets, secrets that may eventually reveal whether we are truly alone or part of a vast interconnected cosmos teeming with extraordinary phenomena. As scientists continue to peer into the depths of the Alpha Centauri system, the discoveries they are making are both astonishing and full of mystery. Among the most intriguing possibilities are objects so exotic that they challenge our understanding of the universe itself. Could these be black holes, neutron stars, or perhaps something even more extraordinary? Black holes are regions of space where gravity has become so intense that nothing, not even light, can escape. When scientists observe unusual signals or sudden dips in light from distant stars or stellar remnants, they often wonder if a black hole might be lurking nearby. The way black holes influence their surroundings can produce telltale signs. Powerful jets of particles, intense X-ray emissions, or gravitational effects that distort the light from other stars. Recent observations by the James Webb Space Telescope have detected unusual stellar behaviors that could suggest the presence of a black hole, especially in regions where the gravitational pull appears to be exceptionally strong. Neutron stars, on the other hand, are the remnants of massive stars that have gone supernova. These dense objects contain a mass greater than our Sun compressed into a sphere only about 12 miles across. Their extreme density creates powerful magnetic fields and sometimes emits beams of electromagnetic radiation that sweep across space like cosmic lighthouse beacons. When astronomers analyze signals from Alpha Centauri, they sometimes find pulsating patterns or peculiar X-ray emissions that could indicate the presence of neutron stars. These signals often tell stories of violent stellar pasts and the remnants left behind after cosmic explosions. Beyond black holes and neutron stars, the universe teems with other exotic objects that defy simple explanation. Quark stars, for example, are theorized to be even denser than neutron stars, composed of fundamental particles called quarks. Primordial black holes, remnants from the very early universe, are another fascinating possibility. These black holes could have formed mere moments after the Big Bang, and their detection might shed light on the universe's earliest moments. There are also more speculative but equally exciting ideas, such as the existence of megastructures built by advanced civilizations. These hypothetical constructs could include vast orbiting habitats or harnessing devices that manipulate stellar energy. Such structures would produce unusual signatures, dimming stars, irregular signals, or anomalous heat emissions that challenge our current understanding of natural phenomena. While the evidence remains circumstantial at this stage, each new discovery fuels the imagination and deepens the mystery. The tantalizing possibility that some of these signals originate from black holes, neutron stars, or other exotic objects keeps scientists on the edge of their seats. Every piece of data, every anomaly, adds a new chapter to our cosmic story. And as our instruments grow more sensitive and our theories more refined, the secrets of Alpha Centauri and its extraordinary inhabitants inch closer to revelation. These cosmic phenomena remind us just how vast, complex, and wondrous the universe truly is. In the vast depths of the Alpha Centauri system, the dance of cosmic phenomena is profoundly influenced by the presence of dust, gas, and magnetic fields. These invisible but vital components of the universe shape the environments where exotic objects and mysterious signals originate, acting as both catalysts and storytellers of cosmic change. Cosmic dust, often composed of tiny particles of silicates, carbon, and metals, plays a crucial role in the formation and evolution of stars and planetary systems. In regions where this dust accumulates, it can create dense clouds that serve as nurseries for new stars, or as repositories of material for forming planets. These dust clouds can also obscure or scatter light from distant objects, sometimes mimicking or masking signals from other phenomena. For example, when astronomers observe unusual star structures or transient signals, the presence of dust can complicate interpretations, making it seem as if there are anomalies where there are none. Yet, studying how dust interacts with light and other forms of energy helps scientists decipher the true nature of what they observe, revealing insights into the processes shaping the system. Gas clouds, mainly composed of hydrogen and helium, are equally pivotal. These vast, diffuse regions can give rise to spectacular phenomena. Shock waves traveling through gas clouds can ignite star formation or cause existing stars to flare or change. In the vicinity of exotic objects like neutron stars or black holes, gas can be pulled into accretion disks, swirling maelstroms of material that spiral inward, heated to extreme temperatures, and radiate intense energy. These accretion processes often produce high-energy signals that can be detected across the universe. Sometimes, gas clouds near primordial black holes or quark stars can generate powerful emissions that help scientists identify their locations and understand their behaviors. Magnetic fields weave an invisible tapestry throughout the Alpha Centauri system, influencing how dust and gas move and interact. These magnetic fields are generated by the movements of charged particles within stars and their surrounding environments. They can channel gas streams along specific pathways, creating jets or outflows that extend into space at incredible speeds. Such jets are often observed emanating from black holes or neutron stars, where magnetic fields funnel material into narrow beams that can span light years. These magnetic fields also play a role in shaping the structure of planetary debris disks and can even influence the formation of potential megastructures if such artificial constructs exist. Furthermore, magnetic fields can induce energetic phenomena like stellar flares or bursts of radiation, which may be mistaken for signals of extraterrestrial intelligence. Understanding the interplay between magnetic fields, dust, and gas enhances our ability to distinguish between natural cosmic events and potential signs of advanced civilizations. It also helps explain the variability and complexity observed in signals emanating from the system. In essence, cosmic dust, gas clouds, and magnetic fields are the silent architects of the universe's dynamic landscape. They govern the birth and death of stars, influence the behavior of exotic objects, and shape the signals that reach our telescopes. By unraveling their roles, scientists are piecing together the intricate puzzle of Alpha Centauri, bringing us closer to understanding the universe's deepest mysteries and the potential signs of intelligent life beyond Earth. The James Webb Space Telescope has opened a new chapter in our understanding of how planetary systems come into being and change over time, especially in nearby stellar neighborhoods like the Alpha Centauri system. Imagine gazing into the cosmos and witnessing the earliest whispers of planet formation, the delicate dance of dust and gas swirling around young stars. This is what the Webb allows us to see with unprecedented clarity. In the case of Alpha Centauri, the closest star system to our own, the telescope has revealed a wealth of clues about how planets might form in environments quite different from our Sun and Earth. One of the most exciting discoveries is the detection of vast, cold clouds of gas and dust encircling the stars. These clouds are the raw materials out of which planets will eventually emerge, and seeing them in such detail helps scientists understand the initial conditions that set the stage for planetary birth. The Webb's powerful infrared eyes have uncovered regions of dense dust, where tiny particles are gradually sticking together, forming larger and larger clumps. These clumps are the seeds of future planets, slowly growing amidst the chaotic chaos of the star's environment. Observing these processes in real time allows astronomers to test and refine their theories about how planetary systems develop, moving beyond simple models and venturing into the realm of actual cosmic archaeology. What makes the observations in Alpha Centauri particularly intriguing is the diversity of the planetary nurseries. Some regions show signs of turbulent activity, with gas streams and dust clouds colliding and swirling in complex patterns. Others appear more serene, with dust settling into thin, flat disks that resemble the early stages of our own solar system's formation billions of years ago. By comparing these different environments, scientists can piece together the many pathways that planetary systems might take, from chaotic beginnings to stable, mature configurations. The telescope has also provided insights into the evolution of these systems over time. We see evidence of how the young stars influence their surroundings, clearing out some of the surrounding material and shaping the eventual architecture of planetary systems. This process, known as planetary system evolution, involves interactions between growing planets, residual gas and dust, and magnetic fields that thread through the disk. The Webb's observations are helping us understand how planets migrate inward or outward, how they accrete atmospheres, and how debris disks may persist or dissipate. Furthermore, the Webb's ability to analyze the composition of these disks has revealed the presence of complex organic molecules and water ice, fundamental ingredients for life as we know it. These findings hint that the building blocks of planets, and perhaps even life, are common in planetary nurseries across the galaxy. The presence of such materials in Alpha Centauri's disks raises tantalizing questions about the potential for habitable worlds in our stellar neighborhood. In essence, the James Webb Space Telescope acts like a cosmic archaeologist, uncovering the layered history of planet formation in Alpha Centauri. It shows us how planetary systems begin as chaotic clouds, evolve through dynamic interactions, and gradually settle into stable configurations that might one day host life. Its discoveries are not only expanding our scientific horizons, but also fueling our imagination about worlds beyond Earth, worlds that may someday become familiar, like home. As we delve into the latest observations from the James Webb Space Telescope, a fascinating picture begins to emerge about how planetary systems come into being and evolve over time. One of the most exciting discoveries is the clear evidence of planetary debris, remnants left over from the tumultuous process of planet formation. These tiny particles, often composed of dust and rock, drift through space, forming intricate structures that tell a story of cosmic creation. Among the most captivating features are the protoplanetary disks, vast swirling clouds of gas and dust encircling young stars. These disks are the nurseries where planets are born, and the James Webb Space Telescope has provided unprecedented detail in viewing them. Instead of just faint glimmers, we now see these disks as vibrant and complex, with rings, gaps, and clumps that hint at ongoing planetary construction. These structures suggest that planets are not just static objects, but are constantly interacting with their surroundings, shaping and being shaped by their environment. Within these disks, astronomers have detected signs of organic molecules and water ice, clues that are vital to understanding the potential for life. The presence of organic compounds, building blocks of life as we know it, in these early environments, hints that the ingredients for life might be widespread in the universe. Water ice, often found in the colder outer regions of these disks, indicates that the raw materials for habitable worlds are abundant, and that the processes leading to life-bearing planets could be more common than previously imagined. The observations also reveal other intriguing indicators of planetary evolution. For instance, some disks show signs of clearing, where material has been swept away or incorporated into forming planets. These gaps and cavities are like footprints left behind by nascent planets orbiting their stars. Their presence suggests that planet formation is not a quiet, uniform process, but a dynamic and sometimes chaotic event, with planets carving out their paths amid swirling clouds of dust and gas. Moreover, astronomers have identified features that suggest interactions between planets and their disks, such as spiral arms and dust streams. These features provide clues about the gravitational influences at play and help scientists understand how planets migrate and settle into their final orbits. Such insights are vital because they help piece together the story of how diverse planetary systems, some remarkably like our own, others vastly different, come into existence. In essence, the James Webb Space Telescope has opened a new window into the very earliest stages of planet formation. It allows us to witness the raw materials, the processes, and the interactions that shape worlds. Each new discovery draws us closer to understanding not just how planets form, but how common potentially habitable environments might be across the cosmos. The universe continues to reveal its secrets, one dusty disk at a time, inviting us to imagine the countless worlds waiting to be explored. The recent revelations brought to us by the James Webb Space Telescope are truly transforming our understanding of how planetary systems come into being and evolve over time. For decades, scientists have relied on models that depict the birth of planets as a relatively straightforward process. A cloud of gas and dust gradually coalesces into a star, with surrounding material forming a disk where planets eventually take shape. While these models have provided a solid foundation, the new high-resolution images and spectroscopic data from the James Webb Space Telescope are prompting us to reconsider and refine our ideas. One of the most striking discoveries is the detailed view of planetary nurseries that are far more complex than previously imagined. These disks are not smooth, uniform structures. Instead, they are dotted with gaps, spiral arms, and other dynamic features that hint at a more tumultuous and intricate process of planetary formation. The presence of gaps, for example, suggests that young planets might already be carving out their own space within the dust and gas, a phenomenon that supports the idea of early planet formation, but also raises questions about how quickly these planets can develop and influence their environment. Furthermore, the detection of organic molecules and water ice within these disks provides compelling evidence that the ingredients necessary for life are present at these early stages of planetary development. This discovery supports the notion that the building blocks of life are widespread in the universe and can be incorporated into planets right from their birth. Yet, the distribution and abundance of these molecules challenge some existing models, which predict a more uniform dispersal. Instead, the observations suggest that the chemistry within these disks is highly varied, influenced by local conditions, radiation levels, and perhaps even the presence of already forming planets. Another intriguing aspect is the dynamic nature of these disks. which display features such as spiral arms and gaps that seem to evolve over relatively short astronomical timescales. These observations imply that planetary systems are not static structures, but are constantly shaped by ongoing interactions. The gravitational pull of emerging planets, the influence of magnetic fields, and the impact of stellar radiation all play roles in sculpting the environment. These insights support models where planetary formation is a more chaotic and interactive process than previously thought, involving feedback loops and rapid changes. At the same time, some observations seem to challenge certain aspects of existing models. For example, the rapid formation of large planetary bodies within these disks suggests that planets can grow much faster than traditional theories predict. This has led scientists to consider alternative mechanisms, such as gravitational instabilities within the disk that can accelerate planet formation. These new clues are urging a re-evaluation of the timescales involved and the physical processes that dominate in the earliest phases. In summary, the observations from the James Webb Space Telescope are both supporting and challenging our current models of planetary system development. They underscore the diversity and complexity of planetary nurseries, hint at the prevalence of life-essential molecules from the very beginning, and reveal a dynamic environment that is constantly evolving. These insights are guiding scientists to develop more nuanced, flexible models that better reflect the rich tapestry of processes shaping worlds beyond our own. As we continue to analyze these stunning images and data, we are stepping closer to unraveling the mysteries of how planets and planetary systems truly come into being and evolve across cosmic time. The recent discoveries made by the James Webb Space Telescope have opened a whole new chapter in our quest to find Earth-like planets. These findings are not just about peering into distant star systems, they are about understanding the very ingredients and processes that could give rise to worlds much like our own. Imagine the cosmic nurseries where planets are born, these swirling disks of gas, dust, and organic molecules. The telescope's detailed images reveal that these disks are far more complex and dynamic than we once believed. Gaps, spirals, and clumps dance within these cosmic cradles, suggesting that planet formation is a lively, interactive affair happening on rapid timescales. One of the most exciting implications of these observations is the presence of organic molecules and water ice in the very environments where planets emerge. Organic molecules are the building blocks of life, and their early appearance in planetary nurseries hints that the seeds of life might be sown earlier than we thought. If these essential ingredients are common in the planet-forming regions, then the chances of finding worlds with the potential to support life could be higher. This fuels hope that Earth-like planets, those with the right ingredients, in the right place at the right time, are more than just rare cosmic accidents. Furthermore, the detailed view of these disks challenges our existing models of planetary development. The dynamic features seen by the James Webb Space Telescope suggest that planet formation can be a rapid and interactive process. Instead of slow, gradual build-up, planets might form quickly within these turbulent environments, collecting water and organic molecules along the way. Such processes could mean that habitable worlds might emerge sooner in the life of a planetary system than previously believed. These insights also bolster the idea that habitable planets could be common in our galaxy. If the ingredients for life are widespread and can assemble quickly, then the universe might be teeming with planets that have the potential to support life. This raises profound questions about how many of these worlds might harbor conditions suitable for life as we understand it. Could there be many Earth-like planets scattered across countless star systems, each with their own stories of emergence and evolution? In the end, the revelations from the James Webb Space Telescope serve as a beacon of hope and curiosity. They remind us that the universe is a place of incredible diversity and complexity, where the building blocks of life are more common and accessible than we once believed. As we continue to explore these distant worlds and their birthplaces, we move closer to answering one of humanity's most profound questions. Are we alone? The answers lie in these cosmic nurseries waiting patiently to be uncovered. The recent discoveries made possible by the James Webb Space Telescope have sent ripples through the world of astronomy and astrophysics, fundamentally shifting our understanding of the universe. These findings have opened up new avenues of inquiry, challenging previous assumptions and inspiring fresh questions about the nature of distant worlds and the cosmic processes that shape them. One of the most profound scientific implications lies in our enhanced ability to study the atmospheres of exoplanets, planets orbiting stars beyond our solar system. The advanced instruments on the James Webb Space Telescope allow scientists to analyze the chemical compositions of these distant atmospheres with unprecedented precision. This means we can now detect the presence of water vapor, methane, carbon dioxide, and other molecules that could indicate conditions suitable for life. The ability to identify such markers is a game-changer because it moves us closer to understanding whether some of these planets might be habitable or even inhabited. Moreover, these observations have provided critical insights into the formation and evolution of planetary systems. By examining planets in various stages of development around different types of stars, astronomers can piece together the life stories of planetary systems. This helps us understand how common planet formation is across the universe, how planets migrate over time, and what factors influence their potential for hosting life. Such knowledge deepens our grasp of the mechanisms that create worlds like our own and sheds light on the uniqueness or commonality of Earth's environment. The discoveries also challenge existing models of planetary atmospheres and stellar influences. For instance, scientists are now observing atmospheres that contain unexpected chemical signatures or display physical characteristics that were previously thought to be rare. These anomalies prompt the refinement of theoretical models, leading to a more nuanced understanding of how planets interact with their stars and their environments. In turn, this influences the broader field of astrophysics by providing data that can be used to test and improve our understanding of fundamental cosmic processes. Another significant implication is the insight into the conditions needed for the emergence of life. By studying planets with varying atmospheric compositions and environmental conditions, researchers can better understand the range of factors that might foster or hinder biological activity. The discovery of planets with atmospheres that resemble early Earth or contain potential biosignatures invigorates the quest to identify signs of life elsewhere in the universe. This not only informs our scientific theories, but also guides the strategic planning of future missions aimed at detecting life beyond Earth. In addition, these groundbreaking observations have implications for our understanding of the universe's history and its future trajectory. For example, by analyzing distant galaxies and their star-forming regions, scientists gain insights into the processes that have shaped the cosmos over billions of years. They observe how galaxies grow and evolve, how stars are born and die, and how cosmic dust and gas contribute to the birth of new worlds. These observations help refine models of cosmic evolution, allowing us to trace the universe's trajectory from its earliest moments to its future. The impact of these findings also extends beyond pure science, influencing how we think about our place in the universe. As we uncover more about the diversity of planetary systems and the potential for life elsewhere, our perspective broadens. It challenges us to reconsider notions of uniqueness and rarity, fostering a sense of cosmic connectedness. This shift has profound philosophical implications, prompting questions about the nature of life, consciousness, and our destiny among the stars. Finally, the discoveries made by the James Webb Space Telescope serve as a catalyst for future research and exploration. They highlight gaps in our knowledge and inspire new questions that will guide upcoming missions. The scientific community is motivated to develop more advanced instruments, to explore different wavelengths of light, and to send probes to the most promising worlds. These endeavors will continue to refine our understanding, ensuring that each discovery builds upon the last, gradually unveiling the mysteries of the cosmos. In summary, the scientific implications of these recent discoveries are vast and transformative. They deepen our understanding of planetary atmospheres and formation, challenge and refine our models of cosmic processes, and bring us closer to answering the age-old question of whether we are alone. They inspire a sense of wonder and curiosity that will drive scientific inquiry for generations to come, illuminating the universe's secrets one discovery at a time. The recent discoveries made by the James Webb Space Telescope have the potential to fundamentally reshape our understanding of life in the universe. For centuries, humans have looked up at the stars and wondered if we are alone, if intelligent life exists somewhere out there, or if simple life forms might be scattered across distant worlds. Now, With the detailed insights provided by this remarkable telescope, we are beginning to move closer to answering these age-old questions. One of the most exciting implications is the possibility that life might be more common than previously imagined. The James Webb Space Telescope has revealed that many planets orbit stars in the habitable zones, the regions where conditions could support liquid water. Discovering atmospheres that contain water vapor, oxygen, or other molecules associated with life suggests that the ingredients for life could be abundant across the cosmos. These findings do not confirm the existence of life, but they expand the realm of possibility. They tell us that the universe is filled with planets that have the right conditions to nurture life, and that perhaps life is not a rare anomaly, but a natural outcome of planetary evolution. Beyond simply identifying potentially habitable worlds, the telescope's insights into planetary atmospheres allow scientists to analyze their chemical compositions. The presence of certain gases in an exoplanet's atmosphere can act as signatures, clues that might indicate biological activity. For instance, the simultaneous presence of gases like oxygen and methane could hint at processes akin to those happening on Earth. Such signals, while not definitive proof of life, serve as vital indicators, guiding future investigations and experiments. This evolving understanding also prompts us to reconsider our place in the cosmos from both a scientific and philosophical perspective. If life exists elsewhere, it challenges the notion of human uniqueness, inspiring a sense of connectedness with the universe. It raises profound questions about the nature of life itself, what it takes to emerge, evolve, and survive in different environments. It also invites us to think about the diversity of possible life forms. Would extraterrestrial life resemble the organisms we know, or could it be entirely different, adapted to environments we have yet to imagine? These are questions that stretch the boundaries of our scientific inquiry and philosophical reflection alike. The impact of these discoveries extends beyond the realm of science into the cultural and philosophical domains. They influence our worldview, prompting us to consider the implications of discovering extraterrestrial life, whether microbial or intelligent. Would such a discovery alter our understanding of ourselves, our origins, and our destiny? Would it inspire a new sense of humility, or ignite a quest to reach out and make contact? These are questions that have long haunted humanity, and now, with each new revelation, we inch closer to answers that could redefine our understanding of life itself. Looking ahead, these discoveries serve as a catalyst for future missions and technological advancements. They motivate the design of missions dedicated to exploring potential biosignatures with even greater sensitivity. They inspire international collaborations, uniting scientists and engineers in the quest to find life beyond Earth. These endeavors hold the promise of not only answering whether we are alone, but also uncovering the nature of life elsewhere, if it exists. In essence, the insights gained from the James Webb Space Telescope have opened a window into the universe's vast potential for life. They remind us that the cosmos is a place of endless wonder, filled with possibilities waiting to be explored. Each new discovery brings us closer to understanding whether life is a cosmic accident or a common thread woven throughout the universe's fabric. And as we stand on the brink of these revelations, we are reminded of our shared curiosity, our collective hope, and the profound journey that lies ahead. The discovery of potential signs of life beyond Earth raises profound questions that go straight to the heart of our existence. For centuries, humanity has looked up at the night sky and wondered whether we are alone in the universe. Now, with each new revelation from the James Webb Space Telescope, that question feels less like speculation and more like a tangible possibility. But along with excitement and curiosity come deep philosophical and existential reflections. One of the most fundamental questions is about our place in the cosmos. If life exists elsewhere, what does that mean for our uniqueness? For centuries, many believed that Earth and humanity held a special, perhaps even divine, place in the universe. Discovering life beyond Earth challenges these notions, prompting us to reconsider our sense of purpose and significance. Are we the product of a rare cosmic accident, or just one among many worlds teeming with life? The implications ripple through our understanding of ourselves, our origins, and our destiny. The idea that life might be widespread also raises questions about the nature of life itself. What does it mean to be alive? Is life a common pattern that emerges whenever conditions are right? Or is it a rare and fragile miracle? Philosophers and scientists alike ponder whether life on other planets would resemble life on Earth or be something entirely different. These considerations force us to broaden our definitions of consciousness, intelligence, and existence itself. There is also an existential dimension to consider. If we find that life is common in the universe, it might suggest that life is an inevitable outcome of cosmic processes. This could be both comforting and unsettling. On one hand, it implies that life, including intelligent life, could be out there, waiting to be discovered. On the other hand, it raises questions about the uniqueness of human life and the significance of our civilization. Does the potential ubiquity of life diminish the value we place on our own existence? Or does it inspire a sense of shared kinship with the universe? The possibility of extraterrestrial life also prompts us to reflect on our responsibilities. If life is out there, what ethical considerations come into play? Should we pursue contact? How do we approach worlds that might harbor delicate ecosystems? The discoveries challenge us to think beyond our terrestrial perspective and to consider our role as stewards of life in the cosmos. Finally, the search for life beyond Earth invites us to confront the big questions about destiny and purpose. Are we merely cosmic accidents, or do we have a role to play in a larger universal story? The answers may not be clear, but the pursuit itself enriches our understanding of what it means to be human. It reminds us that our curiosity and quest for knowledge are intrinsic parts of our nature, driving us to explore the unknown and to seek meaning in the vastness of the universe. In the end, these discoveries do more than expand our scientific horizons. They challenge us to look inward, to question our assumptions, and to embrace the profound mystery of our place in the cosmos. As we stand on the brink of a new era in space exploration, the discoveries made by the James Webb Space Telescope have ignited a flurry of excitement and curiosity about what lies ahead. The telescope's groundbreaking observations have opened a window into planets orbiting distant stars, revealing atmospheres that may harbor the building blocks of life. These revelations have set the stage for a new wave of missions and studies designed to delve even deeper into the cosmos, seeking answers to the profound questions about our place in the universe. Looking to the near future, one of the most anticipated endeavors is the launch of the European Space Agency and NASA's James Webb Space Telescope successor missions. These missions aim to build upon the foundation laid by their predecessor, equipped with even more advanced instruments tailored for detailed examination of exoplanets. Scientists are eager to analyze the atmospheric compositions of these worlds with greater precision, searching for traces of water, oxygen, and other potential biosignatures. Such missions will help determine whether the conditions observed are truly hospitable for life, or merely the result of cosmic coincidence. In addition to space-based observatories, ground-based telescopes are undergoing significant upgrades. Large telescopes situated in remote, high-altitude locations are being fitted with cutting-edge spectrometers and adaptive optics. These enhancements will allow astronomers to scrutinize exoplanets from Earth with unprecedented clarity, complementing the data collected by space telescopes. By combining observations from both vantage points, scientists hope to piece together detailed portraits of planetary atmospheres and surface conditions. Moreover, upcoming missions are focusing on the study of planetary systems within our own galaxy that resemble the early solar system. The goal is to understand how planets form, evolve, and develop the potential for habitability. Missions such as the Transiting Exoplanet Survey Satellite and the upcoming Nancy Grace Roman Space Telescope are designed to identify new worlds and analyze their properties. These surveys will expand our catalogue of planets that might sustain life, giving us a broader perspective on how common habitable environments could be. In the realm of technological innovation, scientists are developing next-generation space telescopes with even more powerful capabilities. Concepts for large, segmented space observatories equipped with advanced coronagraphs and starshades are on the horizon. These instruments aim to directly image Earth-like planets and analyze their atmospheres in fine detail, seeking signatures of life in the most promising candidates. Beyond observational pursuits, theoretical and laboratory studies will continue to play a crucial role. Researchers are simulating planetary atmospheres and chemical processes to better interpret observational data. These efforts aim to distinguish between biological and abiotic signatures, sharpening our understanding of what constitutes evidence for life beyond Earth. All these planned missions and studies reflect a collective human effort to push the boundaries of our knowledge. With each step forward, we inch closer to answering one of the most profound questions of all. Are we alone in this vast universe? The journey ahead promises to be as exciting as it is humbling, reminding us that the cosmos still holds many secrets waiting to be uncovered. As we stand on the brink of what feels like a new era in our understanding of the cosmos, scientists are weaving together a tapestry of theories to explain the recent discoveries that have captured our imaginations. These theories are not just hypotheses, they are the threads that could unravel some of the universe's deepest mysteries. One of the most compelling ideas centers around the notion that some of the signals we've detected from distant worlds might be the result of biological activity. Imagine for a moment that life has found a way to thrive under conditions vastly different from our own. Perhaps some planets possess atmospheres rich in gases like methane or oxygen, but in quantities that are hard to explain without invoking the presence of living organisms. Scientists are exploring the possibility that these gases could be signatures of biological processes, much like the way oxygen in Earth's atmosphere is a sign of life. However, they also recognize that non-biological processes can produce similar signals, so the challenge is to distinguish between the two with utmost precision. Another leading theory considers the role of planetary geology and chemistry. It's possible that the atmospheric compositions we are observing are the result of complex, non-living processes. Volcanic activity, for instance, can release gases into a planet's atmosphere, creating signatures that mimic those produced by life. Here, researchers are delving into the intricate dance of planetary interiors and surface interactions, trying to understand how geological phenomena could craft atmospheric fingerprints that resemble biological activity. This line of thinking pushes us to refine our models of planetary atmospheres and to be cautious in interpreting signs of life. A fascinating area of speculation involves the concept of false positives, scenarios where what appears to be a sign of life is actually caused by abiotic phenomena. For example, certain stars emit radiation that can trigger chemical reactions on nearby planets, leading to atmospheric compositions that mimic biological signatures. These processes challenge scientists to develop more sophisticated tools and methods to differentiate truly living signals from those that are merely mimicking life's signatures. It's a reminder that the universe may be more inventive and surprising than we can currently comprehend. Some scientists are considering the possibility that life elsewhere might not resemble anything we have encountered on Earth. Perhaps extraterrestrial life is based on entirely different biochemistry, utilizing solvents other than water or gases other than oxygen and methane. Such ideas lead to the theory that our current detection methods might only be catching a glimpse of the tip of the iceberg. To truly understand what we are seeing, researchers are exploring a broader spectrum of potential biosignatures, molecular signs that might indicate life in forms unfamiliar to us. In recent years, there has also been a surge of interest in the idea that some of the signals could stem from technological civilizations. The notion of extraterrestrial intelligence, often called the search for extraterrestrial intelligence, invites us to consider that some atmospheric anomalies or electromagnetic signals might be the signatures of advanced civilizations. While this remains speculative, it drives scientists to consider all possibilities, pushing the boundaries of our understanding and technological capabilities. A unifying thread among these theories is the recognition that our current understanding of planetary environments is still in its infancy. The universe is an immense laboratory of natural experiments, many of which we have yet to comprehend. As our observational tools become more sophisticated and our models more nuanced, we expect to refine these theories and perhaps even discover entirely new ones. The hope is that with each new observation, we will peel back layers of cosmic mystery and move closer to answering the profound question of whether we are alone. In essence, these leading theories serve as guides, a way to interpret the wealth of data streaming in from distant worlds. They challenge us to think beyond Earth-centric perspectives, to consider the universe's boundless capacity for diversity and complexity. And as scientists continue to explore, analyze, and debate, we stand on the cusp of potentially transformative discoveries. Whether these signals are whispers of life or echoes of geological processes, one thing is certain: the universe is eager to reveal its secrets, and we are listening. As we peer deeper into the cosmos, it's natural for our imaginations to wander beyond the well-established scientific theories and venture into the realm of the fringe. These are the ideas that might seem strange or improbable at first glance, but they often spark curiosity and inspire new lines of inquiry. While the mainstream approach relies on rigorous evidence and testable hypotheses, fringe theories challenge us to consider possibilities that stretch the limits of our understanding. One of the more intriguing notions involves the idea that life might exist in forms vastly different from anything we have encountered on Earth. Conventional science often assumes that life requires water, carbon, and a certain temperature range. But what if life exists in environments that seem inhospitable by our standards? Some scientists speculate that life could thrive in places like the dark, frigid depths of the icy moons of Jupiter, such as Europa, or the sulfurous, boiling pools of volcanic planets. These hypotheses push us to consider alternative biochemistries, life that might rely on silicon instead of carbon, or utilize entirely different energy sources, like radiation or magnetic fields, to sustain itself. Another fringe idea revolves around the concept of shadow biospheres. This theory proposes that there could be forms of microbial life on Earth that have remained hidden from our detection methods because they are fundamentally different from known life forms. These hypothetical organisms might use biochemical pathways that are so alien that they elude our current testing techniques. If such shadow biospheres exist, it could mean that life is far more common in the universe than we think, simply because we have yet to recognize it in our own backyard. Then there are more speculative hypotheses concerning the possibility of artificially intelligent civilizations, or even extraterrestrial intelligences that operate on principles we have yet to understand. Some suggest that advanced civilizations might communicate through signals or technologies that are so subtle or unconventional that they appear as mere anomalies or noise in our observations. These ideas fuel debates about whether what we sometimes dismiss as cosmic background radiation or random signals could in fact be messages from intelligent beings far beyond our current comprehension. A more controversial fringe theory involves the notion of multiverses, an idea suggesting that our universe might be just one of many. According to this hypothesis, there could be countless universes, each with its own set of physical laws and constants. If true, this radically expands the scope of the search for life, implying that life might exist under conditions that are completely alien to ours, in dimensions beyond what our senses can perceive. While this idea remains highly speculative and difficult to test, it offers a tantalizing possibility that life could be more diverse and widespread than our current models suggest. Some thinkers have even proposed that certain cosmic phenomena, like strange signals or unexplained anomalies, might be evidence of extraterrestrial technologies that are so advanced they appear to us as natural phenomena. These hypotheses often border on the realm of science fiction, yet they serve as reminders that our understanding is still incomplete. They encourage us not to dismiss unusual observations outright, but to consider whether they might hold clues to something extraordinary. While these fringe theories may seem far removed from mainstream science, they play an important role in expanding our horizons. They challenge us to think creatively and to question our assumptions about what is possible. In the end, exploring these unconventional ideas keeps the spirit of scientific curiosity alive, reminding us that the universe may hold surprises beyond our wildest dreams. And perhaps, just perhaps, some of these wild notions will one day be validated by evidence, opening new chapters in our understanding of life and the cosmos. As we stand on the brink of new discoveries, the potential impacts on the search for extraterrestrial intelligence are both exciting and profound. Imagine the moment when our telescopes finally reveal a planet orbiting a distant star, its atmosphere glowing with signs that hint at something more than just geological processes. These breakthroughs could dramatically reshape our understanding of what it means to find life beyond Earth. First, these discoveries could broaden the very definition of what constitutes intelligent life. Traditionally, we have looked for signs of technology, radio signals, artificial structures, other telltale markers of civilization. But as our observational tools improve, we might begin to see evidence of life that is radically different from anything we know. Perhaps microbial biosignatures or chemical imbalances in planetary atmospheres could suggest biological activity, even if no technology is apparent. Such findings would challenge us to rethink our criteria for recognizing intelligence and could lead us to consider new forms of communication or interaction that do not resemble human technology at all. Second, detecting signs of life or even simple biological processes elsewhere could ignite a surge of curiosity and urgency among scientists and the public alike. It might motivate a shift from looking solely for technological signatures to exploring a wider array of biosignatures, organic molecules, unusual atmospheric compositions, or even potential biofluorescence. This broader perspective would make the search more inclusive, increasing the chances of discovering life in forms and environments we had not previously considered. Third, these discoveries could influence the development of new technologies and missions designed specifically to probe the nature of extraterrestrial life. For instance, if we find evidence of microbial life in subsurface oceans or in atmospheres vastly different from our own, future space missions might focus on deploying probes capable of directly sampling these environments. Such advancements would enhance our ability to understand the biological and chemical diversity of the universe, opening doors to answering questions about the origin of life itself. Moreover, uncovering extraterrestrial biosignatures could spark a philosophical and cultural revolution. Humanity might begin to see itself as part of a broader cosmic community, prompting reflections on our place in the universe and the meaning of life. It could inspire new ethical considerations about how we approach these worlds and the responsibilities we bear in our quest to explore them. Finally, the potential for discovering extraterrestrial intelligence, whether through signals, artifacts, or other means, would be the most transformative. Confirming that we are not alone would answer one of the most profound questions humanity has ever asked. It would inspire a new era of scientific, philosophical, and perhaps spiritual exploration, reshaping our understanding of ourselves and the universe. In the end, each new discovery acts as a stepping stone, guiding us toward a future where the universe might reveal its secrets. Whether through detecting simple life or encountering intelligent civilizations, these advances promise to deepen our curiosity and expand our horizons, forever altering the narrative of humanity's place among the stars. As we stand on the cusp of discovering whether life exists beyond our planet, the journey forward hinges on some remarkable technological and methodological leaps. Imagine for a moment the next generation of space telescopes, tools so advanced that they can peer through the glare of distant stars with unprecedented clarity. These instruments would need to be equipped with exquisitely sensitive coronagraphs and star shades, capable of blocking out the overwhelming brightness of their host stars, revealing the faint glimmers of orbiting planets. Such precision would allow us to directly image worlds that are eerily similar to our own, even from hundreds of light years away. But imaging alone isn't enough. To truly understand these distant worlds, we must develop new spectroscopic techniques that can analyze their atmospheres in extraordinary detail. Imagine instruments that can detect and distinguish between the subtle signatures of water vapor, oxygen, methane, and other gases, each one a potential clue to the presence of life. These spectrometers would need to be far more refined than anything we have today, capable of teasing out faint signals from the noise of interstellar space. They would also have to operate across a broader range of wavelengths, capturing more information about planetary atmospheres than ever before. Alongside these hardware innovations, advancements in data analysis and interpretation are vital. The sheer volume of data generated by future observatories will require sophisticated algorithms and artificial intelligence systems, capable of sifting through the signals and identifying patterns that might indicate biological activity. Imagine virtual assistants, trained on countless planetary spectra, that can flag potential biosignatures and guide scientists toward the most promising targets for follow-up observations. In addition, laboratory experiments will play a crucial role in refining our understanding of what biosignatures look like under different planetary conditions. Researchers will need to simulate various atmospheres and surface chemistries, testing how biological and abiotic processes produce specific signals. This iterative process will help us develop a more nuanced toolkit for interpreting the data we collect from distant worlds. Methodologically, new approaches to planetary exploration are also on the horizon. For example, deploying smaller, more agile spacecraft that can orbit or even land on exoplanets, performing in situ measurements. These probes could analyze surface materials directly, providing context that remote sensing alone cannot offer. Developing autonomous systems capable of managing these complex missions will be essential, especially considering the vast distances involved. Furthermore, Breakthroughs in gravitational microlensing and other indirect detection techniques might open new windows into worlds we cannot yet see directly. By observing how light from distant stars bends and flickers due to planetary companions, scientists could detect planets that are otherwise hidden from view. Altogether, these technological and methodological advancements promise to revolutionize our quest to find life beyond Earth. They will transform our capacity to not only detect distant worlds, but to understand the stories they hold. Stories written in their atmospheres, surfaces, and perhaps even their biospheres. This relentless pursuit of innovation will bring us ever closer to answering one of humanity's most profound questions. Are we truly alone in the universe? As we stand on the precipice of this new era of discovery, it is essential to consider how these advancements fit into the grand tapestry of human space exploration. For centuries, our curiosity about what lies beyond our own world has driven us to look upward, to send explorers beyond the confines of Earth, and to develop increasingly sophisticated tools to unravel the secrets of the cosmos. Looking back, the journey began with simple observations. Early astronomers, armed with nothing more than telescopes and a relentless desire to understand, noticed points of light that twinkled in the night sky. These early stargazers laid the foundation for an entire field dedicated to exploring the universe. Over time, their efforts evolved from mere observation to the launching of spacecraft, probes, and telescopes designed to peer deeper into the universe than ever before. The advent of space exploration marked a turning point. The Apollo missions, which carried humans to the moon, transformed our understanding of our place in the universe. They proved that reaching beyond our planet was possible, and ignited a passion for exploring other worlds. Since then, robotic missions have become our eyes and ears on distant planets and moons, revealing landscapes and atmospheres that once existed only in the realm of imagination. Yet despite these tremendous strides, the fundamental question remains unanswered. Are we alone? The pursuit of extraterrestrial life has driven scientific inquiry to new heights. Each discovery, whether it be the detection of water on Mars or organic molecules on distant moons, adds a piece to the puzzle. These findings have fueled our curiosity and pushed us to develop even more advanced technologies capable of detecting signs of life in places previously thought inhospitable. In this context, the recent innovations in indirect detection methods and autonomous systems represent the next chapter in our exploration narrative. These tools will enable us to look more precisely and efficiently for signs of life across the galaxy. They are not just incremental improvements, they are transformative, allowing us to survey vast regions of space and analyze the faintest signals with unprecedented sensitivity. When we think about how these advancements fit into the larger story, it is clear that they symbolize our relentless pursuit of knowledge and our desire to understand our cosmic origins. They are the logical continuation of a journey that began with observing the night sky and has grown into an ambitious quest to find companionship among the stars. Each technological breakthrough brings us closer to answering one of humanity's most profound questions. Are we truly alone? This pursuit also reflects our evolving perspective of what it means to be explorers. No longer just passive observers, we are becoming active participants in the universe's unfolding story. The tools we are developing now serve as our instruments of discovery, helping us to read the cosmic narrative written across the universe. They remind us that our journey is ongoing and that every new piece of data, every subtle signal, brings us closer to understanding our place among the stars. In the grand scheme of space exploration, these discoveries are milestones, markers of human curiosity and ingenuity. They connect us to the broader narrative of exploration that stretches back through history, from the earliest navigators across vast oceans to the scientists peering through telescopes into the depths of space. Our quest to find life beyond Earth is not just about answering a scientific question, it is about understanding ourselves and our cosmic heritage. As we continue forward, each step, each discovery adds depth to our story. It reminds us that we are part of a universe that is vast and mysterious, yet intimately connected through the pursuit of knowledge. These innovations are not just technological achievements, they are the next chapters in humanity's ongoing saga of exploration, a story that is still being written, with many more discoveries waiting just beyond the horizon. As we look deeper into the cosmos, asking what our solar system reveals about its uniqueness or commonality among countless others, we find ourselves on an ongoing journey of discovery. Our solar system, with its familiar planets and familiar patterns, might seem at first glance to be a typical example of planetary arrangements. But beneath that surface lies a story far more complex and intriguing. For many years, scientists thought our solar system was a standard template, a model to compare others against. It has a central star, the Sun, surrounded by planets orbiting in nearly circular paths. These planets range from the rocky terrestrial worlds close to the Sun to the giant gas planets farther out, and then to icy bodies and dwarf planets at the edges. This arrangement seemed to fit neatly into a broader pattern of planetary systems, leading us to believe that perhaps our system was just one of many like it. But as our tools have improved, especially with the advent of advanced telescopes and detection methods, our perspective has shifted. We've discovered thousands of exoplanets orbiting stars far beyond our own Sun. Some of these worlds are eerily similar to those in our solar system, while others are strikingly different. We have found planets with scorching surfaces so close to their star that they are molten, and others with icy shells covering vast oceans of liquid water beneath. Some exoplanet systems have planets packed tightly together, orbiting their stars in a matter of days, while others have worlds orbiting at distances so great that their existence challenges our ideas of planetary formation. This diversity suggests that our solar system might not be as typical as we once thought. It might be a rare gem, or perhaps a common variation among the countless planetary systems scattered throughout the galaxy. The answer is not yet clear, but the data indicates that the universe is teeming with a variety of planetary architectures, each shaped by its own history of cosmic events and conditions. One key piece of this puzzle is the concept of habitability, the potential for planets to support life. Earth, our home, sits comfortably in what astronomers call the habitable zone, where conditions might allow liquid water to exist. But when we examine other systems, we see that many planets within their star's habitable zone are worlds we would consider inhospitable, extreme environments of heat, cold, or radiation. Conversely, some planets outside the traditional habitable zone might have subsurface oceans or environments capable of supporting life, hidden beneath thick layers of ice or atmosphere. These revelations lead us to ponder whether life might be more common than we imagine, or if Earth remains a special case. If planetary systems are as varied as the planets themselves, then perhaps the conditions for life are equally diverse. The universe may be a place where life exists in myriad forms, thriving in environments that we have yet to imagine. Understanding whether our solar system is unique or a typical example is more than an academic question. It strikes at the core of our identity and our place in the universe. Are we the product of a common cosmic recipe, or are we a rare and precious exception? The answer influences how we search for life beyond Earth and how we understand our own origins. Every new discovery, every new planetary system we study, brings us closer to grasping this profound truth. As our technology advances, enabling us to detect even the faintest signs of planets and their atmospheres, we gather pieces of a vast cosmic puzzle. Each piece helps us see whether our world is an outlier or part of a grander pattern. In the end, the question of our solar system's place within the universe reminds us that we are part of a much larger story, one that is still unfolding, filled with surprises and new insights. Whether our system is unique or common, the pursuit of this knowledge connects us to the cosmos and fuels our innate curiosity. Are we truly alone or just one of many in this vast, wondrous universe? As we stand on the threshold of these remarkable technological advancements, it's worth contemplating how they will shape the minds and hearts of future generations. The discoveries we are making today are not just scientific milestones, they are profound shifts in how we see ourselves within the vast tapestry of the universe. To those who will come after us, these developments will be the foundation of a new understanding, one that may redefine humanity's sense of belonging and purpose. Imagine children growing up with the knowledge that distant worlds, once the stuff of science fiction, are now within our reach to explore and understand. For them, the universe will be less of a distant, mysterious expanse and more of a familiar frontier waiting to be charted. They will learn that planets orbit stars scattered across countless galaxies, some possibly hosting life in forms we have yet to imagine. This knowledge will inspire a sense of wonder and curiosity that surpasses even our current dreams, fueling a desire to seek out answers that are still beyond our grasp today. The idea that life might exist elsewhere in the universe could profoundly influence how future generations perceive their place in the grand cosmic story. It might foster a sense of humility, reminding us that we are part of a much larger narrative. It could also cultivate a feeling of connection, an understanding that life, in all its diversity, is a shared cosmic phenomenon. Such awareness might encourage a more unified outlook among humanity, emphasizing our common origins and shared destiny within the universe's vastness. Moreover, these advancements could redefine our philosophical and cultural perspectives. If we discover that life is rare and unique to our planet, future generations might see Earth as a precious and fragile sanctuary, inspiring greater stewardship and responsibility. Conversely, if life is found to be widespread, it could bolster a sense of kinship with other worlds and possibly even other intelligent civilizations. The knowledge that we are part of a cosmic community might influence art, literature, and spirituality, weaving these discoveries into the very fabric of human identity. The impact of these scientific breakthroughs will extend beyond academics and explorers. They will shape the stories we tell, the questions we ask, and the values we hold dear. Future generations may grow up with a more expansive view of what it means to be human, viewing ourselves not as isolated beings on a lonely planet, but as participants in an intricate and interconnected universe. This evolving perspective might also inspire a new sense of responsibility, knowing that our actions could someday influence the broader cosmic environment, or even our chances of discovering life elsewhere, could lead to greater care for our planet. It might foster a collective consciousness that recognizes our role as stewards of this tiny blue world amidst the stars. In the end, these scientific advances offer more than just knowledge. They offer a new lens through which to see ourselves. They open doors to questions about existence, purpose, and our destiny among the stars. As future generations look upward, peering into the depths of space, they will carry with them the legacy of our curiosity and our relentless pursuit of understanding. Their perspectives will be shaped by the discoveries we make today, discoveries that will echo through time, inspiring awe, humility, and hope as they continue to explore the infinite universe that surrounds us all. As we stand on the brink of potentially unprecedented discoveries, it is essential to reflect on the ethical and societal considerations that come with the possibility of finding signs of extraterrestrial phenomena. The very thought of encountering life beyond our planet stirs a mixture of excitement, curiosity, and a deep sense of responsibility. These are questions that reach into the core of our human identity and challenge our perceptions of life, morality, and our place in the universe. First and foremost, the discovery of extraterrestrial life, whether simple microbes or complex organisms, would compel us to reevaluate our understanding of life's uniqueness. Would we see ourselves as a special creation, or as part of a vast, interconnected web of life that stretches across the cosmos? Such revelations could inspire humility and a renewed sense of stewardship for our own planet. They might also prompt us to consider the moral implications of our interactions with other forms of life and the importance of respecting their potential existence and integrity. There is also the question of how humanity should respond upon making contact or detecting signs of extraterrestrial intelligence. Should we approach with caution and strict protocols, ensuring that our actions do not inadvertently cause harm or provoke conflict? Or should we be open and communicative, eager to share our own stories and learn from others? These decisions will require careful thought, guided by ethical principles that prioritize safety, respect, and understanding. Establishing international agreements and frameworks ahead of time would be crucial, so that responses are coordinated and considerate of the diversity of human perspectives and cultural values. The societal implications are equally profound. Such discoveries could unify humanity, fostering a sense of shared purpose and collective curiosity. The idea that we are not alone in the universe could inspire a new era of cooperation, transcending borders and differences. On the other hand, it could also trigger fears and anxieties, especially if the nature or intentions of extraterrestrial entities remain uncertain. Ensuring that public communication is transparent, accurate, and sensitive will be vital to prevent misinformation, panic, or misinterpretation. Furthermore, the potential for societal disruption must be acknowledged. Religious beliefs, philosophical worldviews, and cultural narratives might be challenged or reshaped by the discovery of extraterrestrial life. Some may see it as a profound affirmation of the universe's grandeur, while others might grapple with existential questions about humanity's significance. Preparing society through education and open dialogue can help foster resilience and understanding, allowing us to integrate new knowledge into our collective worldview thoughtfully. There are also practical considerations regarding the ethical use of technology and resources in the search for extraterrestrial phenomena. As we develop more advanced tools and missions, we must be mindful of the environmental impact on Earth and other celestial bodies. Respect for the pristine nature of distant worlds and avoiding contamination are ethical imperatives that guide responsible exploration. Our pursuit of knowledge must be balanced with a commitment to preserving the integrity of the cosmos. Ultimately, the journey toward discovering extraterrestrial phenomena is as much about self-reflection as it is about exploration. It challenges us to consider what kind of civilization we aspire to be, one that approaches the unknown with curiosity, respect, and humility. It calls for a collective ethic rooted in compassion, responsibility, and the recognition of our shared humanity. As we venture outward into the universe, let us remember that the choices we make today will shape the legacy of our species and our place among the stars for generations to come.